Okay. Hi, James. Hi, Victor.
Hi. Welcome, everyone. There's, so if you can just, yeah, perfect. Wait, there's feedback here. Give me a second.
Yes, give me a second.
You should just...
Exactly, yeah. Yeah.
Okay. I think, right. I guess everyone can hear me here.
But now you maybe need to put the output.
Yeah, we can.
Yeah, you can hear it. Yeah, perfect. So welcome everyone to day 2 of the Hypermatrix workshop. Sorry for the delay. We're dealing with some unexpected logistical issues with the connections, but I'm delighted to be introducing Liubov. Nicolas Behr is behind me. He'll be speaking later. And so Francesco Lotito had some teaching to do this afternoon, but he will be joining for the final talk of the day. Without further ado, because we are really a bit tight on time, let's go on with the first talk from Liubov. Take it away.
Okay, very good. I'm starting to share my screen with all of you. Very nice to see such an international crowd of people. And I'm okay. Okay. Yeah. So I'm Liubov. I am part of the several laboratories here in Paris, in Balatz, LPI, for Macri, and also I was for some time lecturing at PT Moscow, and I see also some people connecting from there. It's great, very international crowd of people. And I will talk about some topic which we have been working on together with several people, which started actually essentially as a research project on studying the knowledge maps and mapping and embeddings, very fancy kind of trendy topics, sorry, not fancy. And my hope here would be that we can also maybe formalize later some in a more mathematical questions of these problems, because there are some areas there that are connected directly to hypergraph topics. And so essentially there will be 2 parts of the talk. I hope we will get back to the second part, because yesterday we had more talks by Richard and by Victor, yes. And beautiful talks also on the topic of non-associative algebraic structures. And I will hope that we may arrive there, but honestly already in the first part, where I will present how these hypergraph structures may help to encode these multidimensional data structures. That would be also already kind of good enough to talk about that. And so before we dive into that, I wanted to actually show this funny example that I've looked at recently when we met with Carlos a year ago, and he told me about this beautiful topic of arity structures, and I was like, it reminds me a lot of things that I have been facing in my research path. And a long time ago, I was part of this Chomsky's bridge of mathematical linguistic team in university, where we were doing linguistic expeditions, and we were analyzing, at that time it was not called parsing language, but essentially it was parsing language. We were decoding language structures and trying to build grammars. And these formal grammars, they essentially had these beautiful n-ary structures, which Chomsky in generative linguistics created. So the beautiful thing here was that this structure, this Yoklab Aldibara, was formed as an arity language structure. Because in some languages, from Turkish languages, they have incredibly rich structure where you have not only verbs like have or be that can be attached to the verb, but they also can have some other semantic structure. So the basically semantic of some complex structures, they can actually create new meaning. So they are very NRE, and that's something that is fascinating. That will be also related to the topic of the talk. And essentially how I write and why I decided to share it with you was because of two things. In 2023, we published a paper about hypergraph knowledge mapping, where we tried to map millions of papers and do it with kind of an embedding. I will explain what embedding is, but essentially what we were trying to do was to convince everyone that in order to construct some kind of knowledge map from all published materials on, for example, some topic in archive, like for example, Nick publishes his rewriting paper in mathematics and in high energy physics, and I publish it in other subjects, and how this overall progresses the science. So that essentially was a question, and we were trying to study that. And reviewers, for I think the first time in my life, asked really question which I was not able to answer, and it actually led me to another research. And in SAMP here, I put this kind of link also here. We started to discuss why and how by finding matrix of embedding of this knowledge landscape, we could potentially find a proper distant matrix between two data points, which essentially are not embedded in any space, Euclidean space, or we don't know where it's embedded, because data, when people talk now about data, they sometimes do not formalize it, and the word data is kind of ill-defined. So that's just kind of a preamble of this talk, and essentially how it first time it arrived, like 5 years ago when we started to discuss it with Mark, was that we were trying to map a trajectory of a scientist. When scientists start, for example, their path from theoretical physics and then they end up to do study in epidemiology, we essentially wanted to understand whether we could visualize it and kind of do this visualization of science, but not in the way, and study this using theoretical concepts of studying trajectories, right? Like people do here in LPTMC a lot, by mapping this. And state of the art of such algorithms, surprisingly, are very low order algorithms. What I mean by that is that when you map, for example, data, for example, here you see the map that was done by projecting high-dimensional textual data. Well, let's say high-dimensional because you, for example, download Wikipedia and all the Wikipedia articles. And what NLP algorithms usually do, that they assume that these data points are all part of Euclidean space. And then you can somehow, either using either Stisny or UMAP algorithm, you project them into low dimensions. Why you do that? Because you need to reduce what they call redundancy, right? Because typically you first start with a very high dimensional space, right? All Wikipedia articles, for example, right? Or with all these articles in archive. And then essentially when you project them, you apply this kind of relational aspect of 2 points in these high dimensions that will be binary, essentially. Usually there is a big assumption, and there are also many tools for analysis are also essentially very limited to, if you look at these papers on mapper algorithm, which is state of the art of this kind of projection embedding spaces, they're very binary. But then when I started to read more about many other things, and I found out that there were not many ones which would be taken into account the fact that some of these structures, or like structures that I showed in the beginning in the language, or structures in science, they essentially are not having just this binary aspect that they can be kind of not two-dimensional and essentially not even three-dimensional, but n-ary dimensional kind of, yeah, they can be very complex. And then afterwards, also when discussing with other people more, I realized that essentially there are already attempts of people trying to understand when to use high order structures and when not to use. So in this graph, maybe Francesco will talk today at the end a bit more. Essentially, it's kind of semi-supervised algorithm that can be built on top of that, where if we have some high order structure, like coming from biology or technical system, if the number of high order motifs is high enough, like in some kind of these hypergraphs, then you do need to apply some tools and statistical and like the algebraic mathematical tools that will be high order. But for some cases, we will not need them because they are just really low number of these high order motifs. Like basically, if you will apply essentially very complex rewriting systems there, maybe you will learn something, but essentially they are very higher, not really high order. And so that's one thing. And also later on, Kostya also shared very interesting research they were doing also on topology of cognitive maps, and where they also find this kind of high order structures, but how to study them. Sometimes people actually understand that there are not many ways of people studying them. And so essentially, I want to get a bit more concrete on what we will talk about here and what are exactly kind of these data structures that we can essentially, and how we can apply this higher level idea that we need to study data using, in some cases, right? In some cases, what I mean by some cases is when you really do have some, so in this plot, which I'm hiding behind, there were paper where they were studying motifs in higher order structures, and motifs in high order structures, they were trying to show the number of high order structures motifs in some specific hypergraphs, right? And in some hypergraphs, they were very present. So how do we decide, right, in the algorithm that you will need to basically apply that or like systematically find them? So the idea of the algorithm that we are now working on also with one of my students, and we try to kind of more formalize it, and I will explain a bit more the context here, was that if you first find a way to, like, you start with some data, and essentially data is very ill-defined object. I mean, it's not the data which Nick kind of you define later on, so I want to make sure that it's not confused with other ones. Then afterwards, you transform it into some other structure, high order structure, essentially. And then afterwards, you can also go, essentially, usually now algorithm, depending on which algorithm you use, for studying or what they call learning features, right? Features learning algorithms, you just assume a lot of things about the data. You assume, for example, that there is a manifold that can be locally connected. That is already a big assumption. Then you also assume, and this is, I'm talking about UMAP, for example, one of these algorithms. Then afterwards, you assume that there is already a structure that it's essentially, in the case of UMAP algorithm, probably some of you already know the UMAP algorithm that actually essentially tries to learn from your high dimensional data points. So we start from the left to the right, your analysis, and you essentially first, for example, you start with articles, which are data points in your high dimensional space. And you want to learn what are the patterns in these structures, right? Essentially, that's what many people do in topological data analysis, if you look at these publications. But the problem, which we will talk about today here, will be that essentially, first of all, the assumption of this manifold learning sometimes for some data structures is very strong. that essentially the local connectedness of the manifold that you want to learn from the data sometimes is very strong, and it's not true simply. We can talk about this for some benchmark data, which we tried to look at. And then afterwards, that's also, there is something in between the manifold and the data, for which actually maybe these assumptions will not need to be taken, but we do have some methods for analysis. And second thing, which also I was not mentioning so much here, but that there is also hyperparameters for this embedding algorithm, that actually there is not just one method that you apply, but actually a set of methods. And nobody actually can tell which parameters, like it's hyperparameter sets. And to make it even more complex, now people actually do apply some autoencoder models, right, for doing the same thing. So they don't do just manifold learning or stochastic embedding, what they call, right, Tisny referred to that, but they actually apply some more complex architectures. Then they basically projected into some latent space. It's essentially these data structures are projected into the latent space of embedding methods. And then hoping that this latent space makes sense, you actually can afterwards what they call decode the information, and then afterwards kind of, for example, either in the case of models which project or generate structures, they can generate or generalize these structures and decode these methods into generating, for example, content. But there were recent papers that tried to look at the structure of the latent space that was saying that, in fact, right now, these hyperparameters sets for these such models, they need to be somehow found, and there needs to be a very solid algorithm. By solid, I mean that they're often optimized through assumptions that if you have, for example, for the case of UMAP algorithm, the way how it works is that in UMAP you're assuming that number of neighbors needs to be neighbors of the points. If you project your data points, needs to be small in case of the assumption that your data is sparse and high enough, like higher, like it's very empirical. Basically, you need to get a sense out of that. And so on benchmarks data, for example, this algorithm may work in a very, very specific way. So they may work, for example, getting, so what you will essentially do if you, for example, project concentric circles into UMAP. So UMAP will kind of transform your data, will remove noise, and then afterwards you also ask algorithm to put into the hyper edge nodes which are connected within the circle of certain radius. What you will essentially get, you will get two circles, but they're somehow twisted, and that topologically will be equivalent to circles, but essentially you see that this, what we call topologically learned structure by the algorithm and circles themselves, right? They're essentially two objects. So essentially what would be nice to have is a set of measures or invariance measures on this for applied for the right structure, that when we deal with some really complex data, like from whatever, brain cancer, some very difficult structures where we don't know ground truth, that we would be knowing what we are doing. So the idea behind this work that we were continuing to do was that we wanted to test it on very simple benchmark data sets, which exist, to show that how it works here. And also just to show it on the example that I've started to show you, that the way how we do that is that we have some data set, right, which we are encoding using specific coding scheme. That, for example, in the case of Hypergraph for archive data set, we have an edge, a hyper edge, that is encoded as the paper. So paper consists of several set of nodes, which are scientific fields, right? Statistical mechanics, computational geometry, machine learning, and a hyper edge will be a paper. So we basically construct a hypergraph from that, and then we can ask certain questions, right? how is it embedded, what would be the graphical structure, how would it characterize, for example, emergence of scientific fields in this case, and what would be the distances distributions in this higher order structure, right? And how would it be different? Would it be actually useful, first of all, to represent this data set as this structure, first of all, because actually we may not need, as if you remember Lotito's plot that I showed you in the beginning, it may not always be useful to represent it in the structure. And maybe I go too fast if you have any questions of this construction of this data set, but I think it's okay. Right. Okay. So, and we studied this in several papers. We studied projecting mechanisms of such a data set from different perspectives already. We studied it from the perspective of embedding it into a manifold. And right now we wanted to go step back, basically staying at this level of this hypergraph projected structure in order to kind of pause for a second this structure and just to see whether we would be able to learn the same amount of information from this as we would be learning from projecting it on the manifold. And essentially, that is also a general question that people ask when they use any of these embedding methods, that they try to understand whether projecting, or kind of what physicists often refer to as cross-graining, whether you would have the same amount of information that you can learn from this projected structure as from the projected structure in a different way, right? And also which algebraic properties of these hypergraphs you may want to study and highlight here. So I'm talking about here very, very kind of high level maybe structures, but the idea is actually also to show here the very specific. So because the graph is very, very messy, it will not make sense to visualize and look at it. So we, of course, would need to do some level of apply some measures. That's typically what hypergraph community of people doing. And from previous research, we already saw some structures in such a cotag hypergraph or cotag network in this case, which is cotag projection of the hypergraph. So in this case, right, in this case, we constructed a hypergraph by encoding nodes as fields, and hyper edges would be papers. And in this case, we encoded an edge if there is a binary relation and there is certain number of articles in both fields, right? So it's kind of a projection of this hypergraph. And there would be already some sort of a reconstructed knowledge space and reconstructed information from that. But essentially, as we saw also from the paper on motifs in hypergraphs, that in the case of co-authorships networks, also in the hypergraph networks, our hypergraph network falls exactly on this one where the number of scientific fields, and I don't show it here, but I show it in the paper, that there is on average number or average arity of a hyper edge is higher than 3. So our graph would essentially, our hypergraph will fall essentially to this one, right? Where arity basically of an edge would be higher. So essentially it would be this one and not the other one. So that's why, I mean, that was a motivation for us to come and ask, how can we study this high order zoo of structures? And also, second question, which I also started to ask with people like Kostya and his collaborators from MIPT, how, in which cases low order measures still would be applicable, because quite often they lead to misleading cutting of or simplification, oversimplification of such results. And so if it depends, and in a way the answer to this question depends on to which community of people you will talk to. Because, if you'll come to people from rewriting community like Nicolas, Behr, and people like Carlos, they will tell like you need to apply rewriting. And if you will need to, you'll come to people from maybe people who are more in the graph community that will of course tell you, oh, you need to apply the generalized Laplacian and analyze the structure, but essentially they are cutting the structure of a graph essentially, and they are simplifying that, right? So there is no universal answer to that question. And the paper which I really liked on that, so to answer these two questions of, okay, now we constructed this graph and we saw that it definitely has some high arity structure in it, as I showed you statistically speaking. So which methods should I use? And essentially, as we discussed also with Kostya, we maybe discuss later on, there are of course some path analysis, right, and which comes more from differential geometry that you can apply there to study this high order structure in knowledge graph. But essentially, you may not. It may not be necessarily very easy to do it, and I will show you why. So first proposition here would be that we would need to first define the hypergraph's metric structure such that there would be some inherited structures and properties of such projections. What I mean by that we construct a hypergraph, and we construct it from data essentially. In this case, for example, it's a knowledge hypergraph from archive papers, right, H. And we impose a metric on it. Metric, by metric, I mean a distance, a notion of a distance, which can be defined through a line graph that is well-studied structure, or through a click graph. And essentially we project, or like we define a metric, and people from Wolfram Institute discussed it beautifully. And there are people who are kind of using, and they are creating a sense of knowledge, kind of, there is a knowledge already on this field of how to define a metric on a hypergraph. But what if we then afterwards project this hypergraph? Because there are, as we will show, we will probably see also from Nicolas' talk tonight, there are some situations when already make algorithms running on graphs, just graphs themselves, they can already be very complex to calculate. So sometimes it's inevitable to project these structures, right, into graph structures. And so in some cases, we would need to be, in this case, in this realm, right, we need to use and study only projected versions. So in which cases metric introduced on that structures would actually be making sense in like give you the same results as a metric on the introduced on the hypergraph. And a second way and a second proposition that I wanted to discuss with you was this idea of encoding hypergraphs as algebraic structures, which we discussed a bit with Ward, who couldn't come today, unfortunately. But there is this crowd of people who discussed and developed what they call non-associative Bernstein algebras, which essentially encode your graph structures. In case of graph, right? I'm not talking about hypergraphs, graphs here. They encode them as a certain algebraic structures as a direct sum of U and Z, defined as a set of all pairs introduced for each edge, where you would have two vector fields, which would be taken from the set of nodes and set of edges, and that would be introduced on edges and nodes for graph. And essentially, I haven't found yet the generalization of the dimensional algebras for hypergraphs yet, but you can extend it at least for ternary hypergraphs. So the ones where you have ternary edges, and essentially this hypergraph, graph Bernstein algebras are used or have been used by physics mathematical community to encode them for studying isomorphism properties of graphs. So the idea, and I think that I wanted to discuss with you, but I don't have so much time, I think, was to understand whether these structures would be essentially valuable structures for encoding hypergraphs. And this is an open question, which I don't really have yet an answer. Only kind of the sense that you can pretty much everything that you know is true for Bernstein algebras for graphs encoding may actually also be extended to some extent to this ternary. I mean, the graphs, hypergraphs only with ternary edges, hyper edges. Sorry. Essentially, it's only because of this commutable multiplication which you can extend it, which by the way, Richard, I need to show you because it's very similar to what you were showing yesterday at the talk. But yeah. And finally, maybe, I mean, it's not finally, but hypergraphs, which we talked about before, and it's something that I needed to also thank Rygarodzki, also people to point out this paper where, you know, there is ways to project, of course, and encode. I don't like the word projection here in the sense because you are encoding the hypergraph representation as a bipartite or clique or line graph. A line graph is a structure where you encode a hyperage as this triploid, actually, Richard. I didn't hear from people the word triploid, but essentially triploid in the case of hyperage would be an edge that you substitute by a node in the center of the hyperedge. So that would be an analogy. And line graph is a graph where you substitute an edge with a point here in the center. And then afterwards you want to count a path, make a path on the hypergraph, you substitute it by a path in such a line graph, and that would be one of these representation of a graph. And essentially what we were calculating and estimating and then comparing to the people from Vasilieva and people who were studying kind of benchmark data of hypergraphs versus line graph projections. They were comparing, and I was trying to do the same for knowledge graph. What they were trying to compare was this difference between weighted hypergraph distance and distance in a clique projection. And so interesting thing was that the number of nodes pairs of the differences of the nodes pairs, like there are 51,000 of 576 pairs, which would be giving you from 0 to 33% of the difference. So there were basically very small number of differences of dyadic kind of pairs. For some specific hypergraphs, you don't really care so much whether you treat them, as I showed you, as a hypergraph structures. But for some, I think this one was this structures from hypergraph. I need to see exactly the name. Enron email hypergraph, where it would actually, they would make a difference, like there were social networks versus the email network structures, where there would be a big difference how we define it. The matrix structure on a hypergraph, and the line graph distance, which people typically are okay with calculating, would lead you to some other response rather than the clique projection. I mean, clique projection, I didn't define it, but clique projection is essentially when you are just counting the hyperage you substitute by the node. Right, so I can refer to the paper maybe from the MIPT group where they calculated it for other benchmark data, and for me, I got essentially big differences on the hypergraph structure for constructed for edges as hyperedges as cliques or line graphs. And essentially also for comparing these graphs, hypergraphs metrics versus graph metrics, one can always try to find other ways of estimating the differences between these two objects and not use this kind of cruel projections that sometimes lead to really big differences, like in the case of like projections of the click versus non-click projections. But like basically you need to be very careful with projections. That was the message. And so, yeah, I don't want to rush, but I want to have time a bit maybe to discuss. So generally, there are many methods where right now people, indeed, we're seeing that sometimes we are applying very, very dyadic and binary logic to this high order motifs presence structures. That can also lead to the development of new algorithms also where we find where this can be structures, where these algorithms need to be applied, not in every case. And for this, we need to also know which matrix structures which we need to encode. And with this, I want to finish, I think, and to open the floor for questions.
All right, thank you very much, Liubov.
Wait, I need to unmute myself. Wait, I will stop sharing because I don't see anything. Yeah, but I'm not sure if there will be any questions.
I think there are. So yeah, any questions?
Sorry.
Any questions?
Yeah, sure. First of all, Luba, thank you very much for your speech. It was really great and very artistic. I wanted to ask you about the Gromov-Hausdorff distances you mentioned in the last slide about the cookbook. Gromov-Hausdorff distance require building some manifold to embed your data structure into. And if it's a hypergraph thing, it means that it's kind of hierarchical and it might have some complex inner structure. So it's a very hard question for me personally. How do you define this manifold? I found Behr theory interesting for these things, but what do you think about it? And what can you give a detailed recipe of this page of your cookbook, if it's okay? Thank you. We can't hear you. You're muted.
Thanks, Kostya. Yeah, actually, so after I was trying to discuss with some people from Behr Labs a lot on this topic, because there were a lot of people who were applying, I don't know, autoencoder for working with a lot of data structures just to try to, for example, encode the amount of information and then, right, to project that and to do it not using some kind of very like basically hyperparameters, right? And these models, for example, can be huge. And so you want to have an algorithm for finding these hyperparameters. And there was this discussion that, oh, maybe we can actually first try to decode the structure, which would be not a manifold like, but somehow learn a hypergraph, how to construct a hypergraph. I mean, it's also a question, how do you construct a hypergraph for that? But essentially the topic came out to talk about the topic of the co-optimal transport. I will post maybe this paper from Nurib's people on this hypergraph co-optimal transport, where they were defining these metric properties, and they were claiming in the paper to formalize common methods for transforming a hypergraph into a graph as maps between the space of hypergraphs and the space of graphs, and studying kind of functorial properties of Lipschitz bounds and demonstrating that this hypergraph core optimal transport would lead for you to be able to compare graphs and hypergraphs in this case, I mean, in our case, for example, right, constructed on the same set of nodes. Because, I mean, what I understand from I really know really little, and there are people in the audience, I should not be speaking and answering this question to you, but they may be. You will try to define this, right, Gromov-Hausdorff distance, which I understand that as kind of generalization of their normal distance, right, is that you first have two sets of nodes and you want to compare them somehow. And the way you do is that you start to grow circles, right, from one set until you reach the other nodes, and you kind of generalize it, and the way
make a filtration.
Yeah, exactly. So, and the same was idea to compare, for example, two matrix structures introduced on two graphs. And so essentially there was in this Redko et al. From New Rips 2021 paper, which is essentially a machine learning conference. I have no idea why. They beautifully defined it, these theoretical foundations of studying what they call hypernetwork measures for different, and comparing these metric structures on different hypergraphs. They claimed that that would work there, and I will post it in the chat, this paper. But if you have, because I know that you know more on that, maybe you can answer your ideas on this and your feeling on this paper. I think it was in neural information processing systems paper. I will post it in also streaming. Yeah, because you used it for hypergraphs as well.
I'm trying. Yes.
Yeah. Okay.
Yeah, with my student, we just a couple days ago constructed several hypergraphs from hippocampal activities, and moreover, we have constructed hypernetworks and studied each level statistics, how they interacted, and well, they're weird. We'll discuss it quite a bit later. And I wanted to ask you.
Yeah.
I want to ask you about the slide about the knowledge graphs on the archive. Did you find an interesting approaches? Because on this graph, it's obvious that you have some community structures, and there are ways to detect them. Like betweenness centrality or something like that. I like geometrical approaches, for example, Ricci flows on these graphs could be very applicable to finding the communities. Did you study, and do you study actually, the community structures separately? Because you got the point, and you say very important things, that globally the graph is, well, its statistics and some invariants are not very well pronounced in terms of distinctions between graphs, but studying their individual community structures, its subgraph structures, some kernels, rich clubs, is a way to learn it, in my opinion.
The kernel?
Yeah, the kernels of the graphs. And rich clubs, which the neurobiologists call it. You mean,
what do you mean by kernels?
I mean the communities of the nodes who have a high amount of edges and hyper edges growing from them.
Yeah, essentially what we did with this paper, I didn't show these results because I kind of already talked so many times, not so many times, but in the initial paper, I talked sometimes, yes, about this on this in this paper where we looked at what they call cognitive distance between fields. And what we looked at was essentially it was not a matrix that we were introducing there, but essentially after we project, for example, some papers, right? It's 1.5 million papers that we, for example, project here, and what we essentially study was the diff distance, but not like a metric distance in our case, right, on this manifold, but the graph distance between each fields, right? Because actually, essentially, there were recent claims saying that essentially science kind of becomes one field again, right? It essentially, if you look at it as a window analysis, it will be looking as if it will be becoming more and more connected. So we wanted to test this numerically, quantitatively, right? And the same we wanted to test on the hypergraph level of the representation, but turns out that essentially both hypergraph and binary structures representation, if you define the cognitive distance as a shortest path or number of shortest path in the case of the very cruel definition of it, an unweighted sense, because essentially it can be also weighted, and if it's weighted, then it may change something. If you define it on a unweighted, for example, case, you will see essentially the same things. It doesn't really matter represented as a hypergraph structure or not. But essentially, if you will go maybe to weighted representation of such a hypergraph, then it may change because it will be different. You will need to account for some differences how you encode these hyper edges, for example, and then there will be a small distinction that will lead to differences. I did not test yet it on the weighted case, and also, there are some sort of questions of also which metrics need to be introduced initially, as we discussed in this SEMF meeting, where we discussed what needs to be a metric, actually why it's Euclidean. Maybe it's not Euclidean essentially initially.
Maybe it's not a metric.
So it's a naive thing to show that it's so in this case, reviewers that they were asking us, they were quite good in saying that, in fact, you should not stop there. Even though like really 99% of papers, it's really, really like even not asked, right? So maybe at some point we will find out that indeed maybe it's not a question to be asked.
Yeah, yes, classics say all dissertations are bred, but some are finished. Thank you very much. Very interesting.
Thank you, Kostya, for coming. Thank you.
If you introduce a metric, we can introduce also visuality. Replacing for each graph, you can replace edges, the vertices by faces and faces by vertices.
But metric on the graph or on the hypergraph or?
The spacing which you see hypergraph in the plane.
Yeah.
Embed them in hypergraph dimensions. And then it's the question whether you get not all the graphs, but like two dimensions.
I don't assume here that it needs to be in. I was not indeed assuming that. Yeah.
Sorry, yes. We're just saying, just your. I don't know why they're still in. It's okay. It's okay.
Because it's coming from the loudspeakers.
Really? Or I switched it off?
Through the HD.
Yeah. Wait. No.
Yeah. So, yes, we cannot hear the questions from here. So I will just relay. So Richard asked whether once there is a metric, if we can introduce a Hodge duality. And so that was the question. Any other questions from the room here? I have one.
Maybe just potentially a bit of conceptual question. So if I understood correctly, you take a problem like looking at a data set of archived papers. Then there's, of course, a curation step where you decide, okay, I'm going to track for each paper which keywords does it cite or whatnot. So in computer science, we say you basically make a class structure. You say there's a class of being a paper, and it has fields which are, and then you decide what data of connectivity you are tracking, or whether it's just having certain sub-properties and so on. At the end of the day, this would, in the simplest case, give you a bipartite graph without any actual extra encoding step, right? You would basically have the type of, I mean, what is it, a paper, and a type of keywords, of which there are different kinds.
Yeah.
And then it seems there's no actual encoding step other than your choice of data scheme, giving you then some kind of fancy typed graph, right? Not necessarily hypergraph, because it's just a bipartite graph, which you could transcribe to a hypergraph, of course. But so I didn't quite get the point. The goal you have is apparently that if you have a data set, you want to analyze it, that if you have two nearby, you want to have a notion of nearby data points, so to speak. So the metric property should be that points that are similar are close, or is that, what is the design goal here?
Yeah, so there were several questions, and maybe I didn't dissect them enough to really, like in the beginning, the first part of the talk, I wanted to focus more on this idea of like
You might be muted, I think.
And then you have to.
Yeah, I have to mute myself.
Yeah, okay. So indeed, if everyone heard the question, but basically the main general question was, why do we sometimes need to care? If I understand well what your question, which type of, for example, metrics or measures we will need to apply on these projections or representations if we are caring about specific encoding, maybe? Or can I interpret your question this way? I mean,
it's more like why saying, I mean, is it the case, because I'm not an expert, that for binary or general separated graphs is still a lot of metrics, so it's usually more hypergraph or
yeah, distance.
I think they call it metric.
Yeah.
I think this is a metric with
Yes. That's why that's why it's also confusing, I think, the way how I wrote it, because I wrote it more or less that the way how you read kind of metric as, oh, you introduce already a metric, but you don't.
Are you trying to construct what's called length space? So you're defining a sample of what things should be close in this notion of length, and then trying to check whether this syntax gives you sufficient properties for length space, or because I guess that's in have perhaps necessarily manifolds is a little bit too much for us. But
it's very good question that you asked, because as you've noticed, first of all, as you noticed already, I did not distinguish between the two here, and it's a big problem in general. I think in this research that needs to be kind of every definition kind of needs to be very well defined here. And second, if you have, for example, the click representation, which I shared here, I mean, I didn't share it, reshare the slides, but the click representation and the high order, bipartite representation sometimes will be enough as a representation of a hypergraph, right? So you don't have to go to other representation. Did I understand well your question? Like that sometimes you don't need to go to the.
How you get from the paper, for example, have at least in the high level description, seem to be automatically a bipartite graph. Basically, the data type you were saying, you have a field of paper, field of keywords.
Yeah.
That's a bipartite graph by definition, without doing anything. But then it seems that much a little bit about your definitions that you want to somehow do data analysis on these graphs.
And also bipartites would be, you mean that it would be weighted in this case, right? Also, I mean, it can be, and
the basic field is quite easy, but I don't know any extra. I mean, the question is how you select what you track of a paper, of course. That's a certain design choice. But in the end of the day, you want to. I thought that the point of your work is to then be able to, well, maybe artificially you want to have some sort of notion of closeness between similar structures.
Sure. Yeah.
Because in chemistry, there is of course a machine learning methods. Of course, there's similar work on chemical graphs in that case. And there's also been works of random representations that basically make similar structures, also similar in their representations. Some interesting work. Traditionally in chemistry, you code them in line notation, so string, which is somehow capable of coding a kind of code. Recently, there has been work on a new encoding called self-piece, which is optimized so that similar graphical structures are also similar in the textual representation. I'm wondering, is that the goal or one of the goals?
Wow. Yeah. I mean, essentially, this discussion started from this whole bunch of literature where people were claiming we visualized how science now looks like. Like there were really set of papers. I don't want to put them now because some of them were claiming that science has a cyclic structure. Like people were really posting this. I don't say that it's pure pseudoscience or something, but it was really interesting that people were posting these embeddings of science papers mapped into like a shape of a sort of certain manifold, and they were saying, oh, now we visualize how science looks like we made a discovery. And so there was an attempt to redefine some methods and to make sure that it's actually not there were no false claims on that, and also to show, because when you embed essentially and when you use encoding with autoencoder models, with whatever models of encoding, I showed also two confusing things maybe here, Nick, because indeed in this case, like the bipartite representation of a paper that we started here was indeed you have a tag and you have a paper. Easy. If you don't have a tag, you usually don't have a tag. Essentially, you have a set of words to a paper, right? So it's essentially all, I mean, we discussed it the first day. There is a finite number, of course, of possible combinations of words in the language. So of course, you can put it this way that it will be a very, very large bipartite graph, essentially, that we need to work on, but it will be too big to work with. So that's why what we do is that what we call tokenization process in this autoencoder model. So essentially what you do is not really, Nick, you can't really essentially design a bipartite graph. You don't work with bipartite graph. That's a problem, essentially, because what you work with is this encoding models where you tokenize your information, and essentially what you are left with is that you are somehow putting in, and that's why I was referring to hypergraph or like manifolds, at least. I mean, it's ill-defined here. I'm sorry for you to hear that, because you are mathematicians, and so you essentially what you are dealing with here very often is not bipartite representation of the papers. Is essentially for each paper you have set of so when you tokenize information. Is a set of numbers that are tokenizing information, and how they tokenize it. There are millions of ways. There is hierarchical tokenization. Tokenization is basically encoding, and it doesn't lead to this bipartite representation. So it can lead to this high order representation, but that's why these methods are essentially interesting. And with recent also papers on the self-regulation of this, in this high order space that you get of a projection, I have a sense that people need more on the also understanding of what structures, tangible structures this can be tackled representing. because often we don't really know. Yeah, but thanks for the classification. Oh yeah.
Yeah, I think maybe I can give you a question because this is like you change that.
Yeah.
Really? No.
Oh yeah. Yeah. Okay. So I think maybe clarifying Nick's question here. You mentioned you wanted something like invariance and maybe use metric in sort of broader sense of some measure, some quantitative measure of your hypergraphs. As you mentioned that you wanted something that was invariant, something can be attributed to the network. So of course, something like a distance or a proximity property would be that. But I think, is it right to say that you wanted maybe possibly something more general?
Yeah.
Okay. So what are you imagining? Like, what are the kinds of things that you want to get in this sort of way? So what are I think Nick referred to distance and length properties and things like that.
Yeah,
What are similar things that you're thinking about that we might help sort of formalize it?
So for example, what we
Luba, you are muted.
Okay, so what already I tried to indeed to point it out, but it was very brief. So I moved the slide very quickly. Because essentially that when you apply this set of measures, when you're embedding your information, and the reason why you embed information in the first place was because usually the amount of information is huge and there is a lot of redundancy to represent, for example, text as a point in 1 million dimensional space. So you usually embed it, right? You usually use some sort of a simplification, right? And people like Carlson and Bernstein would be much better explain that theory than I do, of course. But then, of course, so first, even if you have the best algorithm that will embed your paper, if your information, your data into low dimensional space, imagine that you found this algorithm, it usually has also a lot of parameterization. So are there any properties of these structures, data structures that would be invariant? Invariant, what I mean by invariant, it's also ill-defined. I'm sorry for the using of the words not properly defined here, but in a sense, an invariant that if you are, for example, applying a set of hyperparameters of these methods, this is the first set of hyperparameters of this method, and you're getting one hypergraph that looks like this, and another set of hyperparameters of this method leads to your embedding, which gives you another hypergraph, like a bit different one. Is there anything universal that you can say that you learned about the structure that will not change? Because essentially it can be a good measure. It will be a good. Sorry. Really? No. Okay. Yeah. So that was, for example, that is something that is a question typically that is there something that will be a good measure to look at across this hypergraph? Because usually when people get a hypergraph representing their data structure, they're extremely happy, but then they very quickly get disappointed that, in fact, there are not really good measures that would be measures to characterize something very universal, independently from, for example, method that you are or hyperparameter set that you start with to construct your data. I don't know if you answered your question, Carlos, but.
Maybe just as a follow-up question, so in the end of the day, when all said and done, how does what you call metric on hypergraphs look like? Is it composed of comparing properties of hyperpatches, or what is this data when it is not manifold?
Yes.
Of the distance measure.
Yeah. So usually, I mean, first of all, it's not. It needs to be, as Richard said, that one needs to first talk about the distance that you define a pairwise between 2 points. Yeah, the 2 points, and usually you would either, for example, define it as a shortest path on this line graph, right? For example, and that would be one way to estimate it, for example, right? To define it.
But just to say
yeah, no, but I mean, you take all the paths. Sorry, then afterwards you find the one which you will minimize.
No, so
unless you
know which is shortest, you already know the distance.
Yes, that's true. You need to define a distance. Yes, you need to construct.
Because in graph theory, at least, there's a very good classification of properties that you can ask about, which are first order logic. They typically speak about neighborhoods and counts and stuff like that. And then there's one second order logic where you can ask whether 2 points are connected. For example. Not speaking yet about any distances, but I'm wondering, so essentially what you call a distance measure of some sort would have to be constructed apparently, if I understood correctly, from some algorithm you can perform that somehow explores between, because I can see on one graph or points on a single graph, and they give you some notion of they connected to the same components. Let's say you count the number of edges that to traverse. Yes, maybe there's a window. This is even though it's like the graph. Yeah, but if I compare two graphs, it seems, I mean, after that is joined. So not the one connect, and it seems to have to do something which dangerously looks like rewriting, because they probably have to transform one graph into the other. First of all, make a connection. Now, that conglomerate, then maybe make counts. But I'm not seeing how it's varied in two graphs. I mean, that seems to be quite a difficult task. How can I even compare them? I can write on the existing edges and do some
iterations.
But is that what you're doing, or what exactly are you doing?
So first of all, when you have to, for example, hypergraphs, like just the ones which we get as a representation of our data, for example, and you usually want to have a sense of distance between any of these 2 points, just because it's quite useful. In this case,
the same graph, or
so yes, so no, so there are two things. They are distances on the same graph, indeed. So all distances, all pairs. So basically, you are you're calculating the distance, pairwise distance between all points on the same graph. Sorry, on the same hypergraph. Yes. So yes, you have yes. And then afterwards, you also want to see if you actually designed your two hypergraphs corresponding to the same data set, right? But these two hypergraphs are designed using different hyperparameter set of your algorithm, whether there would be any way, right, also to compare them and not to compare. Okay, then I did not understand your question. And it not
you just make a statistic of, for example, distance distributions.
Yeah, and that's what you do. Yes, and I was asking you as mathematicians, right? As is if
for example, you have this here. This is called evolution. There are skeletons and there are all animals. Then you can ask which animals are close, which are then discover some criteria. A mouse, an elephant, it's closer than a mouse and an size fish.
Yeah.
See that little things are closer and big things are not. But this is resistance. to define such a distance, we need some criteria. You can say that all triangular structures are close to each other, and that's quadratic, and so on. So distance is a very arbitrary thing. It's has to just to have two inequalities.
But on the other hand, nowadays we would probably not even bother to, not in many cases at least, to even define something back then. You would probably ask for a training set and then put this into a graph, right? Or see if things get a bit similar. So, I mean, I'm just saying that probably that's the most difficult part of your project, not find a good notion of distances from hypergraphs.
Yeah. I mean, also
other than the one can guess, yes.
Also because as a previous speaker also was mentioning, that often people, what they try to do is to apply kind of measures from the I don't know, the generalized version of the Laplacian, or like something that you're usually doing in the graphs case. So it's not something that necessarily will be the best. I mean, they basically first project it into a graph, and graphs are typically usually more studied, and there you can maybe make sense more out of that. But essentially, maybe I cannot answer the question of whether there is also, it makes sense to by comparing these two hyperparameter sets, I mean hypergraphs that are constructed using hyperparameter sets of hyperfeatures, which I showed you on this slide, whether they lead to kind of the same hypergraph structure. Because actually maybe if they don't, maybe that method is doing something wrong, because it just doesn't manage to learn and capture something data. And it's typically something that is a big problem in this community. That people ask me, okay, is it a good method, Liubov? Like, I have no idea, but maybe if your method, if you change a bit the set of hyperparameters and it just gives you answer, I mean, it gives you the answer to your question which are opposite, maybe then there is, maybe you're choosing not the right set of parameters. So it's kind of helping to construct this method which will lead to semi-supervised manner, like you want to explore that set of hyperparameters that will be giving you not such a sensitive question. I mean, it's maybe a bit too machine learning. Yeah, sorry for that. Okay.
All right, so I think we can thank you all again. Thank you very much. So we switch speaker, I think. Yeah, perfect.
So I think you.
We try to make. I let them connect to Zoom, probably, no?
Yes, that's the first thing.
Somewhere.
Do you have a password, right, from internet?
Yeah, I had to leave the moment ago. Sorry.
Yeah, let me just share it again, maybe, if you want.
Can you just send again?
Sorry, I had it a moment ago. Maybe I just. Okay, sorry.
You have it?
Yeah.
So I mute myself.
So now. Yeah, because now I'm coming from it. Because when you are connected to HDMI, we are connecting to the loudspeakers. What I could do is I could connect to different audio source, maybe, so that we don't have it on the loudspeakers.
for coming up. I think if you just speak through there, I think we should.
Is that okay? Yeah.
Yeah.
Okay.
It's not going to output your own input. So.
Okay.
From your laptop. So as long as we are muted.
Now the only interesting question is, sorry. That's not better. Sorry. Just for 1 second, this one. Try that again. Sorry, I never tried that new feature. Oof. Oh. Interesting, but why is it not? Does anybody know how to get it so that it's on the same display?
You mean?
It's a new feature / never use it. Arrangement here, sorry, I got it.
Because, okay.
That's much better. So let me just take this one back and again.
Yep.
But
Nice.
okay, that's much better.
Yeah.
And now I only need to share it apparently. And then we are good. Screen, I guess.
Yeah, you just need to change screen.
I'm keeping if you want.
But the online audience sees probably my presenter notes. Oh my God, sorry. I'm so sorry, we didn't test this before, so.
Yeah, I know that it's very confusing with the sharing.
Yeah, sorry.
But it's fine.
So the final question is how
If you want to use the screen.
Can we do it? I give you the connector and you just stream or Zoom screen from your computer.
Sure.
And I can just use this one and I just, sorry,
If you prefer.
otherwise we waste too much time.
I'm happy to do it, yes. So you want me just to share?
Your screen to this our HDMI, so we see the HDMI.
Yeah, I think it's better for you.
And now will the online people see my the title slide?
Yeah.
So I will just need to share the full screen of Zoom.
And then people should be able. Sorry for that.
You cannot start sharing while the other person.
No, you don't share your screen. Sorry, I was misunderstanding. You just put the HDMI cable and then just show your Zoom screen. Sorry,
sure.
That's what I meant.
Sorry, yes. I'm so sorry. I need to. Yeah.
Still not sharing the screen. Sorry, give me one.
I think.
Yeah.
Oh, it is
Okay,
not.
perfect.
So let me try this again.
Okay, you need.
Yeah, I know, but yeah, screen.
Oh, it's not sharing. Sorry.
My God, sorry for that.
Yeah.
We'll get there. Just 1 second. And now,
Yeah.
that seems to be working. Oh, okay. Okay. So should I start?
Let me just say a couple of things. So, welcome everyone. It's a pleasure to redo Nicolas Behr. It's a real pleasure to finally have him present the most presented. We're also giving patents. And and it's a real pleasure and I look forward to the discussion.
Thanks a lot for the invitation, and to say that we already had Greta at our seminar series on buffering. We already hosted both Stephen Waldrom and Jonathan Goraz, so nice to see this is continuing. So I will speak today about something which I feel it's a development in theoretical computer science, which has been going on since about 2014, which was one of my main projects over the last 10 years. And it's about a relatively simple idea at first sight, but which might have some interesting consequences also for many of the algorithms you guys seem to be discussing. And so what I will tell you today is how a so-called compositional writing theory more or less automatically gives rise to certain algebraic structures, which could be of interest. And so of course, then the first question is, what is it itself, compositionality? So what does it? It is a technical term. There's philosophical versions of that term, but I'm going to talk about a certain mathematical sense. And to give you an idea how this arises, let's think of a prototypical example of a system where we manipulate graphs. So for the sake of the argument, for the moment, we are starting from an input graph, which may just be an undirected multigraph, if you wish. And then what I'm showing is a sequence of operations. So I mean, in order to not draw a sequence of graphs, I'm just showing it in one large picture. So this is going to be a sequence of operations applied, and I'm indicating where I'm touching something in the graph. So for example, when I create an edge, I'm telling you with the lines, where am I touching in the graph? Two vertices. There, then I add an edge. I mean, this is this little comic diagram. I maybe continue adding another edge. Maybe I delete some edge and create another. Something very, very basic. Imagine this is an algorithm, a program you're running. And then after, of course, each operation, you get a slightly updated graph. And I guess this is a very, very prototypical situation in many fields of research. And now there's an interesting kind of question one can ask. So as this diagram already suggests, there is some very intricate relationship in principle, causally, between these are very simple rules, and yet there's already something quite non-trivial, you can say, once you go away from looking at stepwise, typically in a data set or in a data stream or in a program, you would have the individual states, so the individual graphs, and between each two graphs, there has happened something, a transition. And then you try to reason about these graphs, maybe put a metric, as Liubov was describing, or something like that, and trying to reason maybe how this changes in between steps. But of course, there's the other option. You can look at the way these transition operations themselves might have causally interacted in the sequence. And what I mean by that, imagine, for example, for a completely abstract sense, you were trying to figure out ways that this little rewriting system could create triangles. I mean, sure enough, there's a certain combinatorics involved because you're in a big graph. And I mean, sometimes you can by accident even create two triangles at once because they're adjacent already V shapes. You immediately create two counts of triangle shape. And one of the interesting viewpoints compositionality offers, in the way I'm going to describe it, is that, well, let's look at the sequence. These are 5 transition steps, and I'm looking at whether at this particular market point, I create a triangle. Well, and I find out there were 2 of these 5 steps that created an edge and then deleted it again. So, I mean, effectively did nothing in a certain way, even though it was not immediately one after the next, but in a way, one could imagine that we might wish to somehow discard this information that there was an edge, because in the end of the day, after these 5 steps, this edge has never been touched, it seems, right? So in a way, in trying to get to some sort of more abstract description how this writing system could produce triangles, I would maybe not wish to mention these 2 guys. And the other guys are really just stepwise creating between 3 points a triangle, which seems to be the canonical answer. How in 3 steps, you are guaranteed to get a triangle between these 3. This is all fine and good. But now somebody else comes and says, well, my graph is not a multigraph, so not one which allows multiple edges. Fine, nothing seems to change. I mean, this is a simple graph. I'm creating some edges. What should happen, right? The problem is now this nice kind of argument I was sketching gets quite a bit more complex, because if you want to create an edge between 2 vertices, well, if there was already an edge, you somehow are not allowed to do this operation, right? So by creating an edge and then deleting it sometime later, you are no longer just doing another round, so to speak, but now the system has information that these two vertices were not connected in the initial state and are not connected in this particular example afterwards. And that is not no information. So the strange thing is somehow that by exploring a graph, by manipulating it sequentially, you are gradually learning something about its structure. So I mean, then of course, immediately the idea comes up, well, somehow could I learn with a rewriting system something about the statistical properties of a graph, for example? And as I was trying to sketch already this dependence on the precise type of graph you are doing, this is not an artifact. It turns out it is very important to know precisely your data structure because it will decide on which kinds of such arguments you might expect to hold.
And do you define the data structure as the initial X0 graph? What do you exactly mean by the data structure?
So first of all, I mean exactly what is our data structure, the graph. A graph itself is not a well-defined term. You have to tell me precisely which kind of graph, hypergraph, typed graph. So as X0, for example, already there, you have to tell me what you exactly mean by graph. And then, of course, the next thing is what can be in the little boxes. I mean, what operations do you allow? There's a very intimate relationship between these two design choices. And I will try to sketch that a bit, simply because to raise awareness that, yes, there's a certain cost to doing the kind of analysis I'm going to show. It has to do with being very exact about the data structures, which is in any event not a bad idea because you're going to program something at some point and you're forced to do it anyway. So, I mean, it's not, but so the kind of the selling point of doing this in the end will be that what is already sketched here in this picture is that there is sort of a interesting property in its own right about these kind of this part of the diagram, which was how these different steps interacted. So the strange kind of wiring diagram kind of structure, which I call tracelets, because it'll turn out that such a shape of 5 steps interacting in some form will be a template for all possible rewriting operations in 5 steps with this particular causal structure on any graph you put. So that will be the feature of compositionality. In a way, the causality of rewriting steps interacting will generate the statistics, or depending on what kind of semantics you use, probability distribution even in a Markov chain of transitions. And what is interesting is that you might think that this has something to do with just, binary relations maybe, and you would be right if it's about certain kinds. If you're talking about multigraphs and other very nice data structures, you can code with some sort of relations between inputs and outputs of operations. But the interesting bit is that already at 3 steps, how they can causally interact, something interesting happens that the output of the first guy drawn at the bottom here has a causal overlap with an edge that one of the endpoints is used intermittently. So if you draw it in one view, like all the steps at once, the causal interaction is actually of a half edge between the first and the third step, I guess, in this picture. Yeah. So in a way, this is already your higher arity popping up right there, because this is not a binary, not a graph morphism anymore.
So just a question, I'm sorry, I want to make too many questions, but you put an edge here between 2 edges when you encoded.
Sorry, maybe I should draw this picture again. So I'm trying. Imagine just each. Sorry, let me run this again. So on an input graph, I'm creating an edge between 2 vertices. I'm drawing on the bottom of a box what is the input motive here, just 2 vertices. And then I'm performing the operation itself, which in the top of the box is I add the edge, right? And I'm just having a shorthand notation to say, okay, I'm saying where I'm attacking the graph. But if I'm attacking with a second step, like for example here, create another edge, something from which was also the output of the previous step, I'm just using a different line color just to make sure. Now I'm, for example, attacking this other vertex there. So the left vertex of the first step is also one of the inputs of the second steps, which can happen, right? They could completely run in parallel, these things, but here it so happens they interact in this way, right? And I'm only keeping, I could have drawn several steps. I mean, after X0 comes X1, which is X0 with 1 edge added. and then x2 is another edge edit in this particular location. But you see, the tricky bit is that what really matters is this could be a huge graph and do everything completely in different places, then this would be boring. But here I'm in a situation where all the 5 steps had some sort of, they touched something which was used before, so to speak, right? Except for the first step, of course. Does it make sense?
And also the order, because you're familiar probably with the way how you read these diagrams.
From bottom to top, yeah.
From bottom to top.
Yeah.
Okay, thanks.
The end result is there's a triangle between the
and well, not only, right? Because what I'm going to highlight to you is that even though your algorithm you'd write for the specific case would be analyzing how triangles occur, trying to explain how triangles occur, and so I'm counting the number of triangles in X0. That's a number. There's absolutely zero information of how the triangles were linked or anything. So how on earth can I go into this detailed picture where I'm rewriting stuff and expect that I get a formula for how the number of triangles changes on average in distribution or whichever?
But don't you do that just full all possible combinations, so it will be too much?
Exactly. So what I'm going to show is how compositionality in some cases can help generate formulas that effectively speak about the partial observation of the graph, namely by pattern counts, but still provide you with some information. For example, if this were a continuous time Markov chain and these steps would happen, basically the randomness is in where you apply the rules and whether you do the deletion or creation thing with some semantics.
Yeah.
So it is some particular kind of analysis, but it goes far beyond that because it also can speak about combinatorics of these writing systems. But maybe I should show that rather than just say it, because I'm sorry, we're stuck at slide 1. Right. So the big picture is that there's many techniques, and my motivation is from the life sciences. I want to understand bio and organochemical reaction systems, but I'm also open, of course, to looking at social network models. And there's many techniques that simply do not have any flavor of profiting from rewriting or transition-based picture, which is strange because many techniques in for example, Markov chain theory work a lot with knowing something about the nature of the transitions. So the main slogan is that graph-based systems are not Petri nets, are not just particle systems with no internal structure. And so the question is, how can you then extend these techniques from Markov chain theory to these transition-based pictures? And I mean, what I propose is that there's something called rule algebra, which is a certain kind of algebraic structure on interaction of rules, which has as a side effect tracelet theory, and I will exactly explain that next, that can translate some of these techniques to this rule-based picture. And then the question, of course, what do you do with it? And I'm going to try to motivate that. And we have nowadays, I mean, as I said, it's a very long-running project, so what we have nowadays is a sort of theoretical framework which is designed so that, in principle, at least for many use cases, you basically look at the bottom of this table. There's a way of deciding whether your particular data type and kind of transformations you're doing fits this compositionality paradigm, I'm saying, without understanding perhaps all the mathematical details which are on the top levels of how precisely we figured out what are the axioms that you need. So rather than, I mean, we could discuss mathematics, but I rather want to show you the kinds of diversity of examples one can already study right now. And of course, I'm very interested to hear if there's particular examples from Hypergraph, manipulation of some sort, then it would be nice to check whether this would fit the paradigm. So one very, very popular paradigm is what's called double push-out for writing. I don't entirely know what's the background of the audience. Just to show briefly, there's an operation. A rule typically looks like some template, which has an input pattern and an output pattern. Think like in this little, I create an edge between the vertices. You are telling me what during the transformation you ask for an input, then you keep some part of it, let's call that K, and then you add some new stuff into it. So for example, previously I chose two vertices, you keep them, and then in the final step add. So it's kind of an internal process where you first delete something from the input and then add something, lose something in for the output. And in order to do that, I have to exhibit what's called a match. So an occurrence of my input pattern in the graph. And then technically what I'm doing is what's called a push-out, complementary push-out. But rather than saying that, let me just show you, I mean, one of my motivating examples from chemistry. Here is a bona fide encoding of well, some kind of organic chemistry, let's say, maybe toy model for it. There's some graphical structures, and in organic chemistry, maybe you know that you never really delete atoms, you just rearrange electron bonds. So it's one of these typical examples. If you take a molecule on the right, that's the input template up top, then you try to apply that in a big molecule, and the transformation itself intermittently deletes some of the edges, but then recreates them elsewhere. And I think that's for the moment, that's good enough as an approximation what writing is. So you see already here, immediately, there's the point of what exactly is the data type. That is a difficult question. Let's skip that to the end. But just to say that I learned from some talk by Maxim Konservich that there's some mathematicians have some situations where they like to clone vertices in a graph because there's algorithms apparently where this is good for. So you might come up with something where you say, take a vertex, clone it into 2 copies, and then add an additional directed edge in it. Motivation being that connected things stay connected. And then here, for example, there's a non-deterministic choice to make. Basically, you clone the 2 vertices and you redistribute the edges originally incident to the one vertex in some consistent, in some way you like, meaning all could go to one or the other. And then, well, you add this extra edge in there. And here is the first hint at what is the kind of analysis that compositionality can give you. Because imagine you start out from a vertex, then you apply in all possible ways the rules. Well, first you just get an edge, but then already there are some ways getting edges pointing all the same direction or different directions and so on. I mean, very quickly you see, if you then, you typically in a program would not get this out of the box. You need to compare graphs by isomorphism. But if you do that, you already get a sort of combinatorial distribution that evolves, that in each generation, you can say something about the number of ways it was possible to reach a certain configuration. And I mean, this starts to look a lot like any other dynamical system you can imagine, only that its basic generator was just one rule. So that's already quite interesting. If you do this...
But it's still discrete.
For the moment. Yeah, for the moment.
It's not continued production.
No, for the moment, it's just a combinatorial analysis you could do. And I mean, already you can imagine that depending, if you have a problem and you compare instances of the problem and you think, oh, maybe it is related to some generation procedure. I can get one from the other through manipulations. It might be interesting to look at how these steps then can interact, right? So one would like to have some sort of causality analysis or other deeper picture than just looking at instances. And this is a kind of analysis that's possible. And I mean, just to say there's other variants. For example, there's a way of cloning where you basically deep copy everybody. So all the edges that go, funnily enough, you then generate the directed simplices and iterations. So in all the isomorphic ways. So
something like percolation, if you have a big graph, it comes here and comes there, and at some point it's not simple connected.
Yeah, exactly. If you do the soap bubble thing, actually, exactly. So when you cut and anybody who was linked to you pops away. Yeah, exactly. Yeah. So that's another kind of semantics called technique is called Scape push out in our language, but it has exactly this feature. Yeah, that you kill connectivity.
There's something like Polish theorem of edges and.
In fact, you can.
The average coordination number.
Yes, for example, if you do tessellation of the plane, there's these 3 von Neumann rules up to the parameterization that you can only perform to keep exactly this Euler characteristic, and that you can also simulate. I've actually worked on that too. So I mean, it's a very, very expressive framework, and I mean, most amazingly, if you look at biological cells. It is simply a fact of this research field that you have some idea of how entities like molecules and enzymes interact. Usually it's not a complete knowledge because simply, I mean, experimentally, it's not well known. And if you look at any research paper in biochemistry, there will be a pure text description which reads something like, I don't know, some wild name of enzyme. If it has that and that site and it is phosphorylated and whatnot, then something will happen. And what I found most impressive, what really drew me into this field was that Vincent Lanos and his co-workers who actually founded or co-founded, I guess, the Cree Institute also, in the early 2000s, they realized that by giving a data structure that can model precisely these kinds of sentences. So it is a data structure where basically you have so-called agents. So these would model macromolecules. About these agents, some partial information is known, that they have certain positions, like your papers, they have certain keywords. And then maybe these positions can even, in biology, they carry sometimes extra datum, or whether they're phosphorylated or not, so they can be modified. And then the key feature of this is that there can be a rewriting operation on this, which does not ask all the information you could have on a molecule. I mean, imagine if you had enzymes which can have 10 different active centers, and on each you have activation or deactivation, and then to write down all the rules how you can get between these two enzymes to just simply link them, or you would have an exponential number of things in the number of sites on each. It is a huge advantage if instead you can just say, I partially observe this thing, and if there's enough information, like in this fraction, I can do a reaction, right? And also later, if I discover there are more sites, this wouldn't even interfere with this. So it turns out that it's so efficient as a language already that this is nowadays the standard of how biochemical databases, or one of the possible standards, how they are called. This is a real life data structure. And then, of course, same idea, to model a biochemical reaction system, you take exactly this coding. Now, of course, you need an efficient simulator. That was what much of the work went into the past 20 years. But then you can do trajectories of such a complex real-life biochemical system by doing local manipulations according to the rules you just gave. But the key point being that these rules only ask partial information. So you only have partial information in the rules themselves. Now, of course, it's interesting once you start plugging many of those together on a concrete sequence, to get a concrete sequence of graph states, you can ask, how did they interact? It'll turn out oftentimes that while for one reaction you only need partial information, once you want to plug them in a certain way, suddenly you need data overall on more of the sites of the enzyme to support a certain sequence of events. And of course, that is exactly the kind of output that you want for analyzing possible targets for drug development or something like that, right? And it's interesting that this Kappa project was quite a success in bioinformatics. There's even a website where you can, a web interface where you can run simulations from a web browser. There's no analysis of compositional properties. So that is still one of the really big challenges in our field. And I wanted to say, in this huge paper, I said, I mean, even though it's theoretical, there's a table, as you can see on page 45, so I mean, it's a long paper, but where for the purpose of sort of giving a database of things you already know support our kinds of manipulations, you have a long list of data structures, including undirected graphs, directed graphs, simple graphs, hypergraphs of all sorts. And also there's a little, it's not yet very, I mean, there's a certain vocabulary of constructions from known cases you can do. If you have a very specific data type, a very particular kind of hypergraph you think needs special attention, because for a hypergraph you have to tell me the vertices of a hyperedge ordered, I mean, like a list, or are they more like a set? I mean, do you not care how they are ordered? Is a hyperedge directed? Can a hyperedge have endpoints and start points, and so on? I mean, and each case warrants a little bit of a different viewpoint, but we give you a list of constructions that, I guess, for hypergraphs, and on top the vertices can have kinds, edges can have kinds. I mean, there's a list of constructions that hopefully give at least a starting inspiration that your data structure might support this. And I think it's important if you write programs to maybe check if it's in any of these, because I mean, it'll give you extra guarantees on okay. For example, if you want to do a continuous time Markov chain based on transformations, which you might want to do, if you want to do a combinatorial argument, your data structure does actually not support this compositionality, then you're basically producing white noise. I mean, to be harsh. I mean, essentially the continuous time Markov chain, you can only partially observe it, typically, because I mean, it's graphs. So then the statistics you get would not be representative of the process if it's not a compositional writing system. That's unfortunately the situation, which is why this might be important in your scenario. And so, yeah.
Just curious, what is the incidence, single incidence?
Oh, it's just because if you have an undirected hypergraph, normally you would speak about the source and target. I mean, it's just a name for, I mean, a hyperedge is incident, it touches those vertices.
So what do you mean simple? What is that? What does simple?
Well, I mean, you might only be allowed to touch. I mean, like double edges. I mean, you might only allow if you choose two vertices. May at most be, I mean, like a hyper edge of a certain arity between them or not. You might allow bubbles or not. You see what I mean? Yeah.
And you say some constructions to categories with recursive properties. So these are two possible just examples.
Yeah, but they give different kinds of structures, and then that immediately influences what kind of rewriting operations you can perform and expect to have a good compositional property. So for example, if you pass from multigraph to simple graph, like in the example in the beginning, then it turns out that in order to have you remember there was this weird feature, if you create an edge and then delete it, for multigraphs this is a null round. I mean, you have not learned anything about the graph. Any two vertices support this sequence of operations. While for a simple graph, only two already disconnected vertices support the operation. So this seems like a conundrum. How would you carry the structure within this compositional picture? And it turns out it's possible because for the one case, you just choose embeddings with no qualifier for the input motives of operation. And for the other, you have to choose what's called regular monomorphisms, so edge reflecting. So if you embed two vertices that are not linked in your domain graph into a target graph, they cannot be linked in the target graph. And that, if you think about it, that exactly explains that once you apply this create and delete sequence, you already know, because there was an embedding of two vertices with a regular monomorphism in the graph, that at this point, these two vertices were not linked. So that information is persistent, which would not be the case if you have arbitrary monomorphisms, because you don't know anything about just embedding two vertices, right? Do you see what I mean? So basically, you go on the list, you see, okay, I have my, let's say, a simple hypergraph, and you already know, I have to be careful. If I want to reproduce this, at least I need to use regular monomorphisms, whatever that is for a hypergraph. I mean, there's also a notion like that. Morally speaking, similar idea. Yeah. So it is a decision grid, so to speak, which hopefully at some point we will elaborate a bit. So if you have any feedback on what is my time budget?
About 25 minutes.
Okay, good. So I'm going to show you briefly, and because I mean, again, this is a workshop on hypermatrix theory and higher arity and so on. So I wanted to show you precisely what is the nature of higher arity, if one can call it that plays a role here. And also to say this is a theory in mathematics, decomposition space theory, which is a very well-established field by now. And one of my collaborators, Joachim Koch, is actually one of the people who really, really pushed this, especially for applications computer science. And it is quite interesting that this very general mathematical theory fits perfectly understanding what is this notion of compositionality we need in this particular kind of setting. And so, again, have a look at sequences of transformations. And I write here, this is double push-out writing, but I mean, imagine it is your chosen semantics. And what we want to understand is if you have a sequence, we go from x0 by applying a transformation to x1. Let's say locally we add an edge, and we do another operation. Go from x1 to x2. So we look at stepwise modifications of graph. And now the point is, what we would like is that we can somehow extract from this how the two rules and quotation marks interacted. So did something from the input of the second rule touch on the output of the first? I mean, mathematically, what we are going to use is called a multisum, but that's not important. Let's imagine there's a way of extracting the smallest graphs that contains the input of the second and the output of the first, so that so together these two embeddings are surjective. So I mean, I'm only keeping everything that I need to find I2 and O1 in this intermediate state, right? So it's the smallest graph that has this property, let's say pre-shift opposites. And then I just take that as, basically I take this intermediate state and just again rewrite forward with rule 1 and against the stream with rule, forward with rule 2 and against the stream with rule 1. This is for reversible semantics of transformation. It might not be in every, if it's not reversible, if I can go against the flow of a transformation, then okay. But let's say here it is. And this gives me this weird looking diagram. So I now have basically the first two lines code for sort of the minimal event sequence that I could have had to see this particular overlap between the output of one and the input of the second. So it's like a minimal scenario where I could have seen this particular causal interaction. And then it so happens to be applied to state x0. And of course, I can forget that intermittently I had two steps and just do I go from x0 to x2 by simply basically composing out these two steps. And now this is exactly the data that you had in these diagrams in the skies. So it's exactly, the top bit is how these two box diagrams were wired together, and the bottom bit is how then they together transform from x0 to the output state. Okay, probably I'll share the slides, it probably takes a moment to go back. And then conversely, so exactly, sorry, where is it going again? Yeah, exactly, I want to get to this state, exactly. I have a structure which shows a minimal sequence, how it's possible to interact in a certain way, and then I just apply that to the input state, directly get to the output state. And conversely, of course, it would be useless if I weren't able to always take this data and reconstruct a concrete sequence of two steps, right? Mm-hmm. So that's basically the reverse direction, which also needs to be possible. So basically then forgetting intermittently how they overlap and just reproducing a two-step sequence that needs to be completely compatible. Otherwise my kind of analysis is a little bit artificial, right? And then immediately, and that is something I found it quite funny because I'm originally a mathematical physicist, and this kind of piece was completely clear to everybody doing rewriting in this particular community. It's called the concurrency theorem for traditional reasons. And that is a structure that was well known in rewriting. Strangely for me as a physicist, and of course immediately you want to play with it, and I mean, you sort of think, okay, if it works for 2, what happens with 3, right? And it turns out here is a problem because mathematically the only thing that is well defined is a binary direct interaction of immediately consecutive steps, like the way we did before. But then you can ask, okay, but now I have this top bit, which is a minimal sequence of the first two guys. That of course has some sort of interaction with the third rule, and I can extract it. Why not? And now all I'm doing is I'm going to, and it turns out, if I can do that also in the other order, first looking at how 3 with 2 acted, and then with the first, I've extracted the minimal derivation sequence now of length 3, and it'll be one of these wiring diagrams with 3 boxes where this new effect can happen, that maybe a half edge of the first guy is mapped into a half edge of the last guy. Right, effectively, if you look at
here, it's simultaneous or not,
well, the steps are consecutive, but I mean, then there will be a possibility to look at things that could have been applied in any other order. But for the moment, they are just consecutive. But the way they interact, when you look at it, you cannot directly look at how 3 interacted with 1 in this picture.
Yeah, exactly. Like here you can.
And now this is an intrinsic feature, it turns out, not just an artifact. So it'll be this decomposition space theory, actually. But for the moment, let's just say we could go on. I mean, as I said, like you should be able to extract this 3-step minimal sequence in either order of nesting of pairwise consecutive compositions. And then extract from it what I call tracelet length 3. So a template for 3-step transitions that has a certain causal order, which is possible, right? And of course, later we will only look at these interactions and not at potentially huge graphs where they could be applied. Okay, and so the trick is that you basically lift individual transitions to a degenerate case of tracelets of just length 1. You just apply the rule to its own input mode. I mean, do nothing effectively, but just have the rule there sitting. But at length 2, you compute the possible partial overlaps of 2 rules, I mean, the output of one with the input of the next, and then complete out these pictures to get 2-step sequences. And at length 3, you choose either order of generation, I mean, either first 1 with 2 and then composite with 3 to get the tracelets and so on. So that defines inductively a data structure, right? And one could say it's compositional because there's nothing in this algorithm that makes anything special about 3. And it's actually easy to prove that you have 2 such minimal sequences. You can stitch them together by choosing an overlap of the overall output of the first with the overall input of the next, and just there's basically a lemma which tells you can effectively just rerun all the steps in this the second sequence to the left and the first sequence backwards, and then compose vertically, and that'll give you a composite thing, which so happens to again have this minimality property of classifying all the m plus n length sequences with that particular causal order. So there's one lightweight thing to say about, in this way it's let's say causally compositional. It turns out there's a much deeper reason this is a data structure that arises and has mathematical properties, and it has to do with precisely our intuition, what we mean when we look at these little wiring diagrams. So imagine now in these 3 boxes, I have 3 operations I want to perform. I somehow think that they are sequentially applied, and I want to ask they somehow interact. Now it's easy to think one thing produced from the first goes into the second. That is not rocket science. And we sort of want to be able to black box and say, aha, and these 2 together have this and that effect, right? And what we want is, this is a sort of persistent structure that anywhere in a sequence of stuff I apply, I can box subsequence of the steps and look at their interior, and so, for example, completely black box them or partially black box them to causally analyze them. And for that to be consistent, what needs to happen is that if I, for example, take the blue black box around step 3 and 2 to produce a composite, I'll produce a wiring from the composite to the bottom guy, and that itself, when I then black box that thing, needs to reproduce the same net effect of the 3-step sequence than if I had just simply applied the 3-step sequence or black boxed another way. And so overall, so if one looks closely, there's 4 projections I can do on a minimal trace by these manipulations. I can produce in black boxes, and I can produce composites of 2 steps sliced into position with another non-black box step. And now there's a very, very powerful concept in mathematics called decomposition spaces. It turns out in this particular flavor, it'll immediately make a link to combinatorial Hopf algebras. So it's along the lines of these ideas of Feynman in particular. So if you look again at this picture and count the number of ways you can extract data from a 3-step sequence by projecting out from any of these shaded regions up there, you find exactly 4 projections. You find the 2 consecutive black boxings, and then a black boxing of how these 2 guys were sliced in place. Basically, you can read out the shaded blue region, pink, yellow, or red, or orange, I guess. And this is not an accident. It turns out this is precisely the mathematical structure at play here. So concretely, sorry, I lost the slide. This is not good. Interesting. Sorry, let me just recover my, oh no. Huh. I'm very sorry, I somehow must have accidentally deleted the slide. Okay, anyways, let's go at this picture. So the 0 simplices in this structure, I mean, so this would be a simplicial groupoid. So basically at each degree, I have a groupoid. And then the objects at degree 0 are just dummy objects, it's one dummy object. At degree, the 1 simplices contain, which are the lines here between, for example, simplex 0 and 1, contain the rules, so the structure that I use to rewrite. And the 2 simplices, the triangles, contain exactly the data of how 2 steps can causally interact to form a net effect composite step. So each of the triangles turns out exactly data of who composition is double preferred semantics. And now the key point is, what then is this weird property that I cannot reason directly on a 3-step sequence, but I have to go through this nesting. But I want it to be that if I compute some minimal representative of 3-step sequence by nesting 1 with 2 and the composite with 3, why should that be compatible with the other way around? Well, pictorially, diagrammatically, it's exactly that if you stick two simplices in this particular way, then one should be able to fill the entire 3-simplex, and in particular also the other 2 phases. That's the statement. And this is exactly done through the concurrency theorem, this back and forth from composites. I can construct sequences and the reverse. So you can exactly go inside this tetrahedron, and by taking, certain pullbacks, pushouts, and so forth, you can do the entire tetrahedron with its interior. Turns out that two adjacent triangles, the two simplices, code for the sequence of 1 with 2 and composite with 3, or the other way around. And the inside is exactly the data needed to mediate between the two representatives. And on the inside, if you see, is exactly this data of a tracelet. So somehow tracelet is something truly non-binary in that sense. It's a true higher order interaction, and it has to do precisely with the statement that it is in interaction with the binary operations, because it codes for possible nesting sequences of binary composition. But it's a true, non-trivial higher order interaction. And if you want the fancy thing, so there is a statement that, for example, what I just showed, that two adjacent faces, I can universally up to isomorphism create the other two adjacent faces, is exactly the statement that this is a homotopy pullback. I mean, I don't know if Xaxis is here, but he might be happy about this. Anyways. Well, and then basically the upshot is that what I call compositionality is basically the guarantee that once you have verified the property at the 3 simplices, that then the higher order simplices are basically obtained by all possible gluings, and there's no internal extra data of a 4 simplex that cannot be recovered from C simplices. So that's what's called a decomposition space of a certain kind. Okay. But long story short, what the mathematicians do not usually do, now in our analysis, we typically, especially if you do Markov chains, we do not want to consider 2 steps different when they are just applied in parallel at different points. So I mean, even though there's of course a sequential order how we saw these steps, we don't really want to distinguish them. So we want to somehow have a notion, pictorially you want to be able to write diagrams next to each other rather than sort of keeping artificially some ordering, right? And on top of that, we usually are not interested, especially if you go into Markov chains over graph-like structures, you have to go to isomorphism classes, it turns out. So in particular, we are not interested in isomorphic representatives of a minimal sequence. And if you plug all of that together, the equivalence by sort of representatives on each graphical structure, the equivalence by what's called the shift equivalence. And on top, I mean, of course, there's one special trace, which is if you do nothing, really nothing. You ask nothing, you do nothing. And you have many copies of that. You probably just don't want to keep more than one copy, right? Or if you parallel execute do nothing, which is a null round in the simulator, with do something, then you just want to keep the do something. Putting all of that together and putting in equivalence relation, it turns out that this particular kind of structure precisely gives rise to combinatorial Hopf algebra. So ordinarily you would just get an algebra, as I will show in the last part of the talk, but this really bona fide gives rise to combinatorial Hopf algebra, and that was, for me, one of the motivations, because I started working with Gerard Shaw and Carol Penson on some problems in normal ordering, which happens to be a special case of these writing systems, which I'm happy to discuss offline, but okay. Anyways, so final bit. So what now is promised effect of having compositionality? What practically do you want to do with it? And here is something which, I mean, I could tell you exactly how to get it from decomposition space theory. So that is now really no longer a hand construction. But I'm going to show you just the algorithmic way to do it, because simply for the first intuition, it's better, I think. So if you give me any such template for rewriting stuff, input, output pair, and somehow what you keep, first step is I will now construct an auxiliary vector space. My vector space will be unusually indexed not by some abstract set or something, but isomorphism classes of such objects. And here, I mean, however you write your input and output graph and how they are connected, it only matters up to relabeling in all of these applications. So let's call that a basis state for a class of such things, delta of R or delta of such rule. And then there's this operation that we saw already pictorially, where now each of these little transformations knows how it can be wired together with others. I mean, you pick a partial overlap morally, and then you evaluate essentially what's the net effect. Once you have partially overlapped, you get a composite rule, right? So you can use that operation to define a binary. So you have a vector space with now a certain binary operation on it, which I call rule algebra product. And it does on basis vectors, again, indexed by subclasses, exactly the sum of all ways to wire together and then evaluating. Now that produces non-negative integer coefficients often, because there might be two different wirings that can produce the same composite rule. I mean, but that's how it is. Again, the operation, you select your semantics for rewriting, you tell me what is this particular overlap structure. But I mean, we can do that for many cases. And this is a picture to have in mind. But that's already interesting. So nowadays we say, because of the decomposition space theory, there's a certain, so decomposition spaces are groupoids. So there's an operation of degroupoidification, which is precisely just taking representatives. And then the binary operation I'm showing here is precisely a convolution product of a certain sense on that decomposition space. But in particular, so I mean, what I'm saying is will not be surprising for mathematicians of this field, but this will give a unital associative algebra already. This is maybe non-trivial, but I mean associative precisely because of this weird tetrahedron type of interaction guarantee. And that was basically something not known in the field. So it's the starting point of any of the other theories you can do with rewriting, I guess, where you want anything like a Markov chain, combinatorics, and so on. And now the second bit is we wanted to do rewriting. This is only just abstract interaction. So how do we get we want to use this now to actually rewrite, of course, right? And here the inspiration came from chemistry. So if you have a chemical reaction system of the very simplest kind, it is a rewriting system on just multisets. Let's say even of just sets here, because I mean only one kind of atom. And it asks, operations are take out an element and add in new elements. And the semantics is that the taking out is combinatorial process of picking from an urn undistinguishable particles, right? So picking one particle is possible in n ways if n is a number of particles. So and the ingenious work of Max Delbrück was to then code that in formal power series calculus. So that was in the 1940s. Basically, rather than giving a very elaborate explanation of how the semantics works in words, we just give a mathematical formula. So we map a state of being in n particles as a monomial x to the n, where x is a formal variable. And we write the operation of how in one step the state should change infinitesimal. Infinitesimal, you have one or no jump. And the only one jump you can do is here take out one particle, make two. And so for a Markov chain, it needs to be the case that the probability mass that you move somewhere else in the distribution needs to be, of course, deduced from the current place so that the net flux is zero probability mass. Well, here's an equation where basically the infinitesimal generator of the Markov chain is expressed as a differential operator. And you see immediately there's something combinatorial going on, because taking derivative dx of x to the n produces you precisely zero. So there's no way of doing that if there's no particle. And n times x to the n minus 1 models precisely the n ways in which you can do a removal. But I mean, you will end up in a state with n minus 1 particles. So now you could think, okay, 400 slides later, you see how a Markov chain for graphs works. But it turns out it's much simpler than that with the algebra at hand. So we need a vector space, which I write in physics notation as ket, which now ranges over isoclasses of the states of the graph that you wish to have. And of course, making contact with the previous example, the only data you have of an isomorphism class of a finite set is the number of its elements, right? So far, so good. And then the real step is, so what replaces the differential operators? Well, you define, we had delta of R was the basis vector in this auxiliary vector space of a rule. Taking now a representation of the rule algebra means you assign a linear operator rho to each of these delta of R. And since it's linear, you only have to say what it does in basis elements. So rho of delta of R on X is defined as a sum over all the ways you can rewrite X using that rule R. And then, of course, by all the ways, I mean the outcomes. You again map that to the isoclasses. And again, you can, of course, get integer coefficients, which are the number of ways you can reach a certain output by rewrites automatically. No extra definition needed. Of course, under the hood, I swiped that this taking isoclasses, there's a non-triviality there, but let's say that's a moral concept at least. And now the real fun part starts to see that this row, if the underlying system is compositional, this row would be bona fide the representation of this rule algebra, of the associative unital algebra, on the vector space of graph states, of graph isoclasses. So it'll satisfy in particular this relationship if you apply in all possible ways one rule, and then to the outcomes in all possible ways a second rule. Alternatively, you can first look at how the rules could have interacted, and then just apply the composites, and you'll get the same distribution. Evidently, it's much simpler if your set X has 1 million vertices, and the rules are typically relatively small. It might be much more efficient to pre-compute the ways the rules can interact before attacking the state. And it gets better because we will, of course, do Markov chain theory in a moment. But just to complete the example, and this is really something, I don't know, for me, it'll turn out as a one-to-one mapping between these formal power series operators and rules. And it is what you expect, because x to the n was used as a basis vector to store the information of having n elements in the set. We will map this to the state of the finite set or finite graph with just vertices, which has n vertices. The multiplication operator with a formal variable will be the representation of the rule that inserts the vertex, and the derivative operator will be the representation of the rule that deletes the vertex. It has, because we're doing linear operators, I only have to show you that the coefficients on the basis chosen match, right? So this is here, because of course there's n ways to pick a vertex and then delete it from a set, right? From finite graph. And in the end of the day, using this rule algebra, on the right-hand side, you have the expression in the language of formal power series operators. And and you see in particular, it's an x squared dx, right? It's not an elementary operation. But then using the representation property up top, I mean, I can just directly translate this as a dictionary shown here, and then use the representation property to get it in much nicer form, which is the one on the left. So the first part of the generator is just the representation of the rule that I chose. Nothing to remember. I take the representation of the rewriting rule that makes my jump. And the second bit is something interesting. It's an operator that takes the vertex, deletes it, and then adds another one. So does another round on a state, but with combinatorial coefficients by a number of ways it was possible to do so. And that will be a diagonal operator. And now if you know something about Markov chains, there'll be a non-diagonal part, which codes for the jumps, and a diagonal part, which has to have the property that the row or column sum, depending on how you orient your vertices, has to be zero, right? It's net flux zero requirement. And so a general Markov chain generator will you choose a set of rules, a set of basic rates. You simply can write down immediately the generator for a Markov chain. And that, in my opinion, and I would even argue that this representation of the autocatalysis reaction, I mean, it's a very clear insight. You take a vertex out, you put 2 in, that is exactly what's written here, right? And then we experimented with this a lot over the last 10 years in many different application scenarios. I mean, sort of the most out there is something we call rewriting theory for the life science, where we show how to do Markov chains for biochemistry or organic chemistry and how to really encode these molecules. We tried a little bit about social network models, but only, I mean, that was more of a technical case study to see if we can use tool from industry for doing rewriting efficiently to reproduce some known details about discrete time Markov chains, like such as the Volta model, which worked. But I mean, we didn't have the application. We really just wanted to see that this technique would be applicable in principle. So it would be interesting to discuss. And then there's combinatorics. And again, like, let me maybe just jump to the last. Can I have 5 minutes?
Sure.
Yeah, because I wanted to show you something, because Markov chains are a little bit tricky because you also have this continuous time aspect. So in a Markov chain, I mean, I claim that this formula I gave has all the definition of a semantics of a continuous time Markov chain, because then you basically run this against, you have a differential equation system and you can run it and you can evaluate observables and so forth. It's a long story, but it is the full definition of a continuous time Markov chain. It's still very counterintuitive, so I thought I would maybe close on a concrete example from combinatorics that just highlights this idea a little bit. But it is similar. Here, the point is we take a data structure, planar rooted binary trees, and I only chose this example because there's a particularly simple way of sampling from a uniform distribution of all possible such things at a certain number of vertices. So if you think about it for a moment, if you want to have a planar rooted binary tree with, let's count correctly, I think 100 vertices, there's 200 factorial over 100 factorial possible ways of having such, up to, I mean, there's noise movement, but, and so a sampling algorithm that gives you uniformly chosen at random samples from, let's say, the distribution of all possible trees at size 100 is heinously difficult. So it's very surprising that there's an algorithm, linear generator algorithm, that can sample this with a linear cost, even though it's growing exponentially in the number of vertices. And the trick is, well, you do a rewriting system rather than a sampling, but a non-deterministic one. So in each step, you have a small grammar of vocabulary of steps you can do. You have to choose at random. And the step is very, very simple. I'm trying to visualize it here. In your current state, you pick an edge, be it the root, the left or right edge kind. You keep the endpoints of that edge, but remove the edge itself. And then you have two options of inserting this little Y-shaped thing. And what I'm trying to visualize is, so the bottom of this Y needs to be of the same kind as the original edge. Otherwise, of course, you might destroy your tree structure. And then there's a left and a right pointing thing. And either the left pointing is the new leaf or the right pointing. And these two options you choose at random. So you choose at random which edge and at random which of the two options. And this will produce you a uniform sample. And you can see, of course, the cost of sampling is, I shouldn't have said linear. Linear is maybe misleading. I meant in each step you have the number of edges in the tree, which is proportional to the number of vertices times 2. But I mean, it's not exponential. That's what I was trying to say. Anyways. And now comes the really fun part. So this is now our generation procedure. And now one can ask, how does this? So I want to convey to you that the kind of arguments one can do here, you probably have seen in some other shape before heuristically. What I'm going to say is that each application will make 2 more edges, right? Something trivial. I can just count. But why can I count? That's his point. And here's where compositionality comes in. So I can look at how an edge came to be in the state after applying the transition. And if it just touches at one of the vertices there, well, I didn't do anything to it. It was there before. It's possible in both directions. Again, like the other point that I kept, whatever was there, I didn't touch it. So that's possible in both directions. But now, if I look at now I have 3 other edges where I can attack. And now something interesting happens because these edges I didn't have before. So on the top, there's 3 candidates where I can edge, right? Which I simply didn't have before. And conversely, on the bottom, I have 1 edge that I delete. So again, like I have the guys that are simply just null rounds. I kept them. But there's 1 edge which I delete. So that one I cannot see on the other order of events. I mean, first applying and then counting. And now the analysis that one performs is so-called commutator. Just as in quantum mechanics, I'm performing a commutator between a diagonal operator that counts edges and I mean, the operator is just a matrix that on each basis state gives me back as coefficient the number of edges. I take the commutator of that operator with the operator that is a representation of this particular rule. It turns out the commutator doesn't see these things that are commutative, and it just gives me back the 3 options to get an edge. Overall, I'm just applying the generator, though. I mean, it doesn't modify the shape of the generator. And 1 option before. And now I see, indeed, an equation that says the commutator of this, first count and then create minus first create and then count gives exactly a coefficient of 2, which is the net win in number of edges. You can replay that game for higher tree patterns. You can compute these commutators. You get wild-looking equations, which causally can be explained through trace sets, but maybe that's another step. But what is the benefit? Now we can use that to give an evolution equation, because what I didn't say is basically there is a way of computing evolution equation on formal power series with this. Let's maybe just skip to the take-home message. And in the end of the day, what I can extract is a formal evolution system which will track the counts of 4 different kinds of patterns, which are shown here. So Y shapes, left come with 2 leaves, I guess, and left with 3 leaves, and also the number of edges. And each time I apply a generator, this will consistently change any given tree state with a certain quadruple of counts to another quadruple. And the interesting bit here is, it turns out that 2 of them are always linearly dependent on just the number of generations, how many times I applied the generator. But the other 2 have a very, very interesting joint probability distribution. And I'm showing here how if I iterate all the possible applications of the generator, because that's what this equation encodes, I'll get a probability distribution, a discrete support one, over the inhabitations of the possible combination of counts of having 2 versus having 3 leaves on these comb-shaped trees. So, and what I want to emphasize is, so at 100 steps, which is where this ends, the support in the space of the original data structure is of cardinality 200 factorial over 100 factorial. So 10 to the 217 possible states. This here is a joint probability distribution over 2 dimensions, which covers all the possible data you could measure on that system if you were to run any algorithmic experiments. And clearly, it's not. It's not even the shape of the support is, of course, not Euclidean. Also, the shape of the distribution itself is not. I mean, of course, it finally will approach law of large numbers at some point. But I mean, here I can show it to you at any intermediate state. And so for me, one of the very important questions here is, if you have any system evolving over graphs and do that analysis on it, one possible analysis is to select a number of observations you do, like in quantum mechanics. Here the observation is counting patterns and trying to reason about I marginalize the full distribution over all possible graph states, which I can never handle because it has too high dimension, by just giving the counts of certain patterns. If I choose this in an ill-defined way, it'll be meaningless because these equations have to close algebraically in a certain way. So it's not easy to construct such communicating sets, if you will. But if I do, then I have a system that is produced from my original system, and which has a property that for these properties that you track, you get the exact same distribution or evolution in a Markov chain. And so that seems to be a powerful tool, and we would be extremely interested, we as in the people I work with, to see if, for example, the analysis of networks by any hypergraph properties, if they can be described to local patterns, might exactly be an example of such type of analysis. And just to conclude, so, I mean, I've shown you some interesting perspective. This was for the rule algebra part of things. To say that it is still somewhat obscure, even though trace sets are needed to define this rule algebra, through these higher order, these decomposition spaces. It's not the case that I've ever seen any direct application of trace sets, let's say any approximation techniques or other, in practice. So there's a high chance of low-hanging fruit, so to speak, that when you're doing a network analysis and you're talking about something like the sequence of events that seems to be dominant to produce certain click shapes or so, that would probably be a tracelet statement. And also one of the other bottlenecks here is that while we now have a very good theoretical understanding, a very solid Markov chain theory, combinatorics, generating functions and such, and we have this little catalog for data structures and what could be compositional, we do not yet have proper implementation of these techniques. So that is a bottleneck. We might attack it soon. I mean, there's some group in Budapest I'm discussing with. But of course, as always, if there's any need from practitioners or any ideas, concrete data types we should try, that would be a very good discussion point, I think. And I suppose I'm well over my time, sorry.
Yeah,
so thanks a lot.
Thank you very much. Thank you very much.
Sure.
Wait, I bring the graph
position of say molecule 3 or 4 coordination numbers. We're using for structural classes and classes. And it is a very successful application of it.
That sounds very interesting. Could you maybe send me a reference?
Sure.
Yeah, thank you. Yeah.
It's just a stochastic matrix. All this gluing is because there are energy barriers.
Right.
So you have to put Boltzmann factor. Not only the statistical, you have to. I just show you.
Yeah. So maybe we can even put the camera.
Glasses.
I mean, maybe it's 40 minutes.
One of the structural glasses is.
yeah, we have things before.
Okay, so not after.
We show axis concentration. So selenium, this kind of glass usually they put ceramic.
Okay.
So the 3 component. And you know what it is used for?
No?
Photocopying machine. It's called glass. It's like a sheet, which is photosensitive because of selenium. So the sheet is rolling like this. And this machine is so when you make a photograph, you put something and there's a flash of light, but before it goes to the chamber when you have made the photo, it is charged negatively.
Right.
So it's an isolator, so it keeps the charge. Now, when the light goes on, selenium has this photosensitive effect, but the electrons went out, go out. But there is no light, electrons stay. The charge is
and then you.
So then you get something that is like a negative. Negative, which is the charge is where it's black, and there is no charge when it's white. Then it goes to another chamber, and black powder is put on, and where the black powder goes, where the charge is. So if there was no light, the powder will stick. If there was light, no. Then you go. There's another chamber, and it's heated in order to make this powder go into paper, and you get it. So that's it. So this glass is elastic. It's fantastic. So this glass is made of selenium, which is 2 valence, and arsenic, which is 3 valence. So suppose the selenium goes with selenium. Tends to make spaghetti. So if you make a pure glass of selenium, it's like spaghetti. It's very brittle. This makes it, first of all, it makes it more random. There is no
more branchings.
branching, and also stabilizes. So now you have. So the idea was to check how it takes some energy to create this bond, another energy to create this bond.
Right.
And yet another energy to create this bond. So, yeah. So whenever you can have already something that's structured. Right? And so on. So you can always say this, there's a bulk and the rim. On the rim you can have the following situations. One like this.
Because we have a talk.
Okay. Sorry.
Next person, because then we can discuss afterwards.
Yeah, sorry.
I mean, because as always, this is a hybrid, so he's waiting. I'm sorry.
Sorry. Yeah.
No.
There is another person waiting. No.
So I want to. There's a couple of questions from the chat. So you can either read them or I can.
I can't see them right now, but
You can see them? Yeah.
no, I can't see them.
Oh, you can? And they're in the Zoom chat.
Yeah, but on this view, I don't see.
Oh, you don't see them. Unrelated. So first question is, can you think of dual vectors in the vector space representation of roots as patterns in your choice of data structure?
Francesco Lotito.
Sorry.
What do you mean by, because that's an interesting question, exactly. You mean, what precisely do you mean by dual vectors?
Again, the dual vector space, show.
I mean, what you can do is, because we are doing essentially stochastic mechanics, so I mean the version of quantum mechanics adapted to not having Hilbert spaces, but L1 summable sequence, so on. What you can do is you can ask a linear operator that counts a pattern, and then have it followed by an operation that sums coefficient. I think that's probably the next to what you want to be a dual, because I mean, you can do Hilbert spaces, but then for the basis I showed, it would be really just pairing isomorphic graphs. That is probably not what you want. Although that could exactly count, of course, the exact graph coefficient, but I guess what you rather want is to count, I'm not sure, maybe you want exactly that. That would work.
Maybe the other question. The other question is, are you aware of any string diagram constructions, bracket pictorial manifestation of compositionality, with rewriting rules replacing linear maps and hypergraph patterns replacing textual?
Yeah, I mean, basically, anybody coming from string diagram, especially from that X calculus, will know this work by Pavel Soboshinsky and collaborators Fabio Zanassi, Fabio Gaducci. Sorry, I'm forgetting somebody. There was a bunch of people who wrote 3 iterations of 3 issues of string diagram rewrite theory. So anything you can do with string diagrams can actually be phrased in a certain kind of rewriting theory, and it's exactly on a certain hypergraph category. It's a little bit technically intricate because the way to get it to compose the way you want, you should read it. I mean, there's something about to plug 2 string diagrams together, there are some constraints you have to respect, but effectively string diagram rewriting or manipulation is exactly compositional rewriting theory. Yeah.
And one final question for myself. I was just curious, when you say you have one of these rule algebras, so say it's some unital associative algebra, how much can you use the classification theory of associative algebras to speak about the causal properties of?
I've frankly never quite thought about that, because I guess usually you wouldn't consider algebras. Are you talking about finite associative universal algebra? I mean, with finitely many generators?
Yes, or any.
Because these here would typically be infinite dimensional. So, I mean, I'm
infinite dimensional.
Because so the generators of the algebras are finite, but I mean, you start out from a finite set of rules typically, but then you start composing them. And so in the full algebra, you have any possible. I mean, you can look at just the algebra generated by individual rules, but then this Lie bracket you construct, for example, might not close. So the set of generators, there are some sub-algebras that are finite, where really you just pick a number of rules, take their commutators under this particular, the Lie bracket under this particular product, and you find that it is a closed algebra. But this is not the general situation. In general, it's countably infinite dimensional.
Okay, so the question is a bit more general in the sense that because if I see something like an associative algebra, some strong algebraic structure, like a half algebra or something like that, my question is more generally, do you have an intuition of how much you can use algebraic theory of these objects to somehow get insight on the causal properties of some rewrite systems?
Yeah, this is an interesting.
The data structures themselves, right? That's what you mean by causal structure.
No, so the causal structure of the rewrite system.
I mean, so the weird effect was, so in the beginning, we looked at, for example, just the Heisenberg-Weil case, where you have the generation of a vertex, the deletion of a vertex, and then in the Hopf algebra, the only non-trivial diagram can have is creating a vertex and then afterwards deleting it. That's the only non-primitive element, right? And then any sequence of events where you can just create and delete vertices will look at a decomposition of parallel creations, parallel deletions. So in the beginning, when we just looked at that, we thought, yeah, okay. So then you look at techniques used in Hopf algebras and basically look at the primitive and the ideals and whatnot. But here, I mean, the interesting bit was that, like I showed in this example with the trees, the commutators here are performing. They give some algebraic coefficients. It doesn't give any insight whatsoever. I mean, by the looks of it, it's quite unclear how on earth these wild. There are rules that basically take a large graph and just manipulate it in a slide position. That didn't seem to shed any light. Once you, however, remember that it all came from these interactions that are stacked together, you can actually visualize where these individual pieces come from and give a causal explanation. So my feeling is that it's really these tracelets that can give you explanations that you couldn't have seen in just algebraic theory, simply because the origin of these particular coefficients and algebra, I mean, the structural coefficients of the algebra are from causality of sequences of rewrites.
Sure. And
so that is, but I'm not saying even after 10 years that we have any, I mean, we have a few selection of examples which, if these commutators are really closed at first level, just the Lie bracket is really close, you usually have everything you could imagine intuitively explained. If they close at a second order, if you have to take nested Lie brackets to get any sort of algebraic closure, intuitively it's clear you need to speak about two-step sequences that can give rise to the contributions. And in fact, I think for Richard's model, I wouldn't be entirely surprised if one looks sharply at it and sees that certain interactions, I mean, sticking to the boundary and then sticking somebody might be a sequence that is interesting to look at. But I'm saying this from the pure theoretical computer science side. Our best guess is these tracelets, but yeah, I mean, I'm sure because these graph manipulations are so ubiquitous, people have had their own developments of how they explain some notion of causality. And
yeah.
Thank you. I have many questions.
Okay.
Well, now because
Yeah.
Maybe let's move to Francesco's talk.
So if you disconnect, probably you should not make any.
Yeah.
Francesco, welcome.
Ciao, ciao.
I think you're muted there, so
I'll just disconnect. Sorry.
I think you're gonna have to.
Yeah, I can't disconnect now because I have to at the same time to be timekeeper for the lecture. Can you connect first?
Okay.
In or
If it was a USB.
Yeah.
So very nice. Thank you for the talk.
Oh, we had tracelets.
Yeah, I also remember you told me about this model.
Right. So Francesco, can you try saying something?
Okay. Ciao. Can you see my screen?
Yeah.
Yes. Wait. It's yeah. So, is there any chance that you can increase your local volume? Your local.
Can you hear me?
Better. That's better. Yeah.
Okay.
Okay. Yes. So, welcome everyone to the final session of day 2. Just as a reminder that we were doing a sort of more rewriting or hypergraph themed day. Yesterday we had a more binary algebra themed day. Tomorrow we'll have a more of a tensor or hypermatrix proper themed day. So our final speaker is Francesco Lotito. As you can see from the screen, he is one of the developers of HypergraphX, and at the Wolfram Institute, we're very excited to have you here at last, as we had some chats last year in Vienna in the Network Science Conference, and I think we are one of the few people in the world who are busy trying to get software to rewrite hypergraphs and do some nice analysis of hypergraphs. So it's a delight, and the floor is yours.
Thank you, Carlos, for the introduction. Thank you for inviting me here for these talks. So yeah, my presentation I think is a bit different in the sense that I'm present mostly something that is very hands-on, like a Python library to deal with higher order networks and hypergraphs, and I will briefly give you a background on the more like theoretical and physics oriented background, and then I will dive into like some like tutorial and examples on how to use this library. What are we developing? What are we developing also in the next future? So I wanted to start like spending a couple of seconds telling you like a brief introduction to networks. So we know that a lot of real-world systems can be usefully described by using networks because they are made of unities that they interact. Of course, networks are a good model for this. And we have examples of these systems of interacting unities in a lot of domains, from social networks, because we have people communicating, exchanging mails or being friends on Facebook and so on. But we also have networks on, like in biological domain, from protein-protein interaction to neural networks, and of course also other artificial systems such as coauthorship networks, co-citation networks, and web and so on. So the idea is that we want to understand these systems, and we usually mean for understanding systems some common tasks, for example, ranking nodes in a network, so understanding what are the important nodes for some definition of importance. We usually want to perform clustering on nodes, so understanding what are groups of nodes with similar characteristics or that interacts a lot in the nodes, and less frequently with nodes outside their groups. Or usually we are also interested in the dynamics on networks, so how things, let's say, move over a network, for example, spreading of a disease, and trying to understand this dynamics on networks. I usually focus more on the structured networks because I have a background in computer science, so I'm more oriented in studying the structure of graphs and so on. So we used a lot of these tools from mathematics, like graph theory and so on, to understand real-world systems using graphs. But and this is fundamental to understand why we are talking about hypergraphs in this context, is that nature is not as simple, and sometimes graphs are poor representation of some systems in the real world. For example, we want to understand the direction of an interaction because it's fundamental for us to understand if node A send a message to node B, or if node B send a message to node A, and we need to put somehow an arrow to the interaction. So we want to remember what was the direction of the interaction. And we cannot use like standard graph for this, because graphs are just vertices connected connected to each other, so just lines. So usually we complicate things by adding a direction or adding some labels to the edges. For example, labels that capture the intensity of an interaction or the temporality of an interaction, if we want to understand, I don't know, if an interaction occurred at 4 p.m. or at 4:5 p.m. or at 4:30 p.m. But sometimes can be useful also to encode the modality of an interaction. So for example, if I send you a message on Facebook, is different than if I send you a message on WhatsApp, or if I send you an email. And to understand some system, it can be interesting, or it can be sometimes fundamental to encode more information. So to encode this information, we have more sophisticated mathematical objects. So we use directed graphs. So edges are now allowed to have a direction. We can use also weighted graphs, in which edges are allowed to have a weight, or temporal graphs. So edges are allowed to have a temporal label, or multigraphs or multi-layer graphs, in which edges are allowed to connect the same nodes, but being discriminated by a label. So having the same edge repeated a lot of time, but with different labels. So the general theme of network science in this context is we want to capture more information about the system we want to understand. So we use more complicated mathematical objects, because we get more expressive power, so we can capture more things about the real world. But of course, we pay the cost of having a more complicated model. We have more complicated algorithms, more complicated software, of course, and we need to cope with this increasing in the complexity. And so there is this sort of balance. So we want to capture more things, but we pay the cost of having a more complex model. And sometimes it's also not that useful to have a more complicated model if we don't get that much in as a return. So it depends on the system we want to study. But there are systems that benefit from this more like sophisticated models. So as of now, we were discussing only about pairwise interaction, and pairwise interaction are very common in the real world, but they are not the only kind of interaction that we can have. And group interaction, and by group I mean multiple nodes that are active at the same time, and they are interacting at the same time. And this can be very common in the real world. For example, co-authorship networks are made by group interaction, in the sense that we have nodes that are the authors of our papers, and the interaction are the papers. So multiple authors write a paper at the same time. We can also have other example of affiliation networks. For example, I don't know, people buying some stuff online, so an order could be made of multiple objects at the same time. But we can also have some example of prey-predator networks that are like made by group interaction, or also examples from biology where we have complexes of proteins. So in nature, it's common to have also this group interaction. And going back to what we said before, sometimes we want to capture in our models also this complexity. And this can be very important to capture this complexity, because, for example, I wanted to give you this example in which I have multiple parties and people going to parties together. And we notice that if we want to model this system with traditional networks, so traditional graphs, and to model with traditional graph, we need a binary relation. So we can use a binary relation, for example, when two parties together. We get these very complicated graphs in which we cannot really reconstruct anything from the original structure of the parties. And so what we do is we move to, as always, to another mathematical object that is now able to encode this group interaction without losing information. And we use hypergraphs. So hypergraphs are a generalization of a graph, of course, in which we have vertices, but now interaction edges can involve multiple nodes at the same time. Yeah, they are not limited to pairwise edges. Okay, so each hyper edge is, of course, defined as a non-empty set of nodes. Of course, graphs are just like a particular case of hypergraph in which each hyper edge has cardinality too. And we notice that now our party system, let's say, can now encode it without losing information using a graph, because each party, so party 1, party 2, party 3, which is made by a number of nodes that is larger than 2. So we have Sarah Ross Anderson for the first party, we have Sarah Ross Drew Elliott for the second party, Ross Elliott Keith and Ellison for the third party. So we have like larger set of people participating to a party together. We can model with hyper edges this party, and we encode like the right amount of information that can be useful. It depends on our task, but at least we know that we have all the information available and we have encoded it into an hypergraph. Instead, in our graph, we notice that we lose a lot of information because we cannot even recover the number of parties that we encoded if we consider only our plain graph. So we know that, for example, Sarah and Ross went to a party together, but we don't know what other people were together to Sarah and Ross at the same time. So, but in our hypergraph, we are able to recover that information. So we call this higher order networks because we want to encode these group interactions. And usually me and my group, we work a lot on hypergraphs. So we use hypergraphs to model these systems. Of course, hypergraphs are not the only way to represent group interaction or higher order networks. In the past, we used a lot bipartite graphs to model this situation in which we have nodes representing the actual unities of these systems, and also we have other types of node representing the interaction. So we could link like group interaction to nodes using like a lower order representation of using a graph. Another popular tool is simplicial complexes, which is as you know, a very established mathematical framework from algebraic topology. And it's also very common to use simplicial complexes to model group interaction, so to encode group interaction from the real world. But the problem, I mean, not a real problem, but like an assumption, is that we also have the closure with respect to phases by definition. And in some physical system, for example, people meeting face-to-face interaction, this assumption can be very restrictive, because if we have, for example, a group of size 3 of people talking to each other, it's not, it's a bit restrictive to say that also we have all the other interaction of size 2 existing in the system. Sometimes we can use simplicial complexes without worrying that much. Sometimes they are they have this limitation. So in my group, we focus on hypergraphs that we believe are the more flexible tool, and also like more oriented to my background in computer science. Instead, simplicial complexes is more like popular in the mathematical community in network science. And of course, we have more tools that can be also sometimes efficient from a computational point of view, sometimes not, sometimes they can useful for some tasks. So we have the tools from algebraic topology that can be can be useful. So we don't discard simplisher complexes, but like we need to choose the right model for our system. In the case of bipartite graphs, this is interesting because in the past we used a lot bipartite graphs to represent higher order networks, but to like in modern network science, let's say we prefer hypergraphs because traditional problems are better represented on hypergraphs than bipartite graphs, and also like the generalization is easier sometimes going from like graph network definition of problems to hypergraph hypernetwork definition of problems. But bipartite graphs and hypergraphs are more or less equivalent from like modeling point of view when representing real world systems. So just to summarize a bit what we said so far, we used a lot of networks to represent real world systems so far, and networks are made by dyadic links. But then we realized that networks would be like a not so good model for some real world systems. So we added a lot of complexity considering direction in the interaction, weights, temporality, and the type of the interactions. But some years ago, we realized that also we wanted to study and to encode explicitly the groups and consider also not only pairwise interaction, but also considering groups without relying on lower order representation networks, but encoding directly groups. So we started to use more sophisticated mathematical objects such as simplisher complex, bipartite graphs. And I want to stress again, in my group, we use a lot hypergraphs to model this complexity, to deal with this complexity. And the key takeaway is that, as always, we gain more expressive power using these tools because we encode more information. But we need to pay the price of having to deal with more complexity. So we need to develop new algorithms. We need to develop more complex statistical tools. We need to develop new also software. So I wanted to highlight this review. One is more like a general, one is one focuses on the physics of higher order interaction. They are very interesting to have an overview of the field. But in the latest years, the number of works dealing with hypergraphs exploded, or higher order network exploded. So we have like a lot of interest in this stuff as of now in the field of network science. So the field is really hot, and in like this huge amount of work, we also wanted to stress about the importance of having like a software to manipulate and analyze this hypergraph data. And of course, like software are really important. Think, for example, about the importance of network X or other tools that we have to deal with networks, that without these tools, it will be very, very difficult every time to re-implement everything that we need for our work. So we believe it's very important to have like a set of developed tool, open source tool that you can easily use. But dealing with hypergraph in the software domain is not that easy, because it's not trivial to understand how to store hypergraphs in order to perform computation. So what data structures should we use to implement hypergraphs? But also it's very hard. Other simple tasks that on network can be more simple. For example, it's hard to visualize hypergraph, and it's also very hard to design algorithms on hypergraphs and make them efficient, especially is very, very, very hard. Another thing that is very important is having data that you can analyze and you can like benchmark your software solution or your new algorithms, and it's very important to have a set of data already made and easy to use. So we tried to put some effort in this in this case, to develop a library to deal with hypergraphs, with the idea of having a set of tools to construct, visualize, and analyze hypergraphs that should be made open source, of course, so people can contribute, use our stuff, and build their scientific work on top of that. We want, of course, to make the library very user-friendly and accessible. So we made a lot of tutorials to use our framework. So every time we have some paper implemented using HypergraphX, we try to have like a tutorial to use our new tools in the library. And of course, we wanted to have a repository of data. So now I want to get a little bit hands-on, so how to install the library, how to use the library, so to have like an overview of what you can do with HypergraphX. So let's start by the intro, the installing the library, which is very easy. We tried to make it very easy, so you can install using pip in Python. And of course, you have like very basic functions. So you can create an hypergraph. So giving nodes and adding edges is very easy. So you have this hypergraph object, and you can add through list nodes and edges. You can, of course, add the weights, and you have functions to get the edges in the hypergraph, to get the weights. Should be very easy to perform this basic operation.
Francesco, just one question. Are your edges lists by default in terms of the data structure? Are they ordered or unordered by default? Can you?
Yes, they are sets. So yeah, there is no order in this case. So basically, we in whichever order you put the edge, we let's say store it in a way that it's unique. So yeah, it's stored as a set basically. So as of now, we don't have like an ordering on like by default we don't have an ordering, but you can also impose an ordering on the edge. You have a parameter, but in that case, like for example, if you have an edge 1,3, it will be different from an edge 3,1. So you can set a parameter, but by default, the edges are unordered. But I think I will discuss a bit later on in this sense, because it's a bit more, we are working a bit on this, so yeah.
And and you implement everything on Python, right?
Yeah, everything is in Python, yes.
Okay.
So you have some also basic operation, like I can query the hypergraph and say, oh, is the hypergraph connected? And you get false or true, like this basic operation on query operation on hypergraphs in the similar way that you have on Network X, for example. We are working a bit also on the drawing hypergraphs. So for really small hypergraph, this can be done, but for larger hypergraphs, this is a mess. We are working on this, but it's not easy. But for the purpose of this tutorial, we can also visualize our hypergraph. So we have like our hypergraph that is not connected. So, but we can also add edges to the hypergraph. And for example, here we add a new edge that connects the two connected component, and we can draw it again. And now the hypergraph is connected, of course, just to give you some example of what you can do. We also spend some time in having this metadata associated to vertices, which can be useful in real world analysis. So for example, you can add some attributes to the vertices. For example, here I added an attribute role to node 1, and I mentioned that the role of node 1 is being a student. So now I can retrieve the metadata associated to nodes, and I get that object 1 is a node and has the role of a student. Another package that we have, like basic package, is generating graphs and hypergraphs. So for example, you can generate random hypergraphs. So you specify the number of nodes and the number of edges. And if you specify also the number of edges for each cardinality. So I want like 5 nodes in cardinality 2, 5 edges in, sorry, 5 edges of cardinality 2. I have 2 edges of cardinality 3. I have 2 edges of cardinality 4. So you can generate these graphs and visualize them. Of course, this is a random generation, but we also implemented some more some more complex generating models, so you can experiment with the generation of random hypergraphs with different algorithms. So I wanted to take like a real world example. So we use a real world data about interaction in high school. So we have interaction of different sizes of face-to-face interaction of different sizes. So interaction 3, 2 of size 2, 3, and 4. And experiment with some packages in the library, so we can understand like from like hands-on point of view what I can do with a real world data set. So we have, of course, this data. We have some different distribution of higher order degree for every interaction size. But something more interesting that I can do that on this package is performing motif analysis on this hypergraph. So I have like real world hypergraph. I want to understand what are frequent pattern of interaction in this large hypergraph. So by motif, I mean I select like a small number of nodes, for example, 3 nodes, 4 nodes, and I count the number of occurrences of each possible pattern of interaction of this size 3 or 4 or 5. So in this case, I selected 3 nodes, so I cared about patterns of the size 3, and I computed basically the occurrence of every possible pattern of interaction of size 3 in the dataset. So I have 6 possible patterns with 3 nodes, and considering both low order interactions, so the first 2 patterns, but also both lower order interaction and higher order interaction, so both interaction size 3 and size 2. And I have 4 possible patterns in the orange interaction. And yeah, we can count these interactions, these patterns, and we have different abundance scores. So basically, with respect to random hypergraphs, how much a pattern is frequent in my real world data. And we get that triangle are very popular. So pattern number 2 is popular in our high school data set, but also interaction like the simplex, let's say, made by 3 nodes, and one group interaction of size 3, and the triangle. So in pattern number 6 is very, very popular. Also pattern number 5 is popular because we have interaction size 3 and lower order, 2 lower order interaction inside the group interaction. But for example, we see that a group interaction without any following lower order interaction inside is unlikely to happen. So people interact in group, but also likely interact also in a pairwise fashion in this face-to-face scenario. If you are interested in our paper, we explored more domains, and we see that this situation is very common in face-to-face domain. So we get these results also in a primary school data set, also in hospital data set, in which we have people interacting in an hospital, but also at conferences. So this behavior of people interacting in group is common in multiple domains, but in other domain is different. So we have different patterns in co-authorship data, for example. So another thing you can do with HypergraphX is performing community detection. So we have multiple algorithms to get communities that also like analyze both interaction size 2, but also analyze the hypergraph structure. So they consider group interaction. For example, here we extracted 3 communities from our data set, and we see that how the communities are structured. In this case, we used an algorithm that is able to get also overlapping communities. So nodes are not assigned to a specific community, but are assigned like with different scores to multiple communities. That's why we have the pie chart for each node. An important task, I believe, that in Hypergraph is very interesting is also to get rid of noise somehow. So we also implemented this paper from Federico Musciotto. This paper here from community detection was from Martina Contisciani and collaborators. This one is from Federico Musciotto and collaborators, and we have like we try to filter interaction based on their statistical significance. So basically we sparsify our hypergraph. So we start from a very dense hypergraph, and we get rid of non-significant interaction. And so you can notice that we remove a lot of interaction. We get a smaller hypergraph that has only statistical significant interactions. And this can be useful, for example, in the visualization. So you have an hypergraph that is very complex. If you get rid from a lot of interaction, and you remain only with the important interaction, let's say, can be interesting because sometimes also algorithms are very inefficient on hypergraphs, and you may want to have like a smaller hypergraph and perform your analysis. Yes, I mentioned that visualization is very difficult on hypergraphs, and yes, we tried to visualize this high school data set, and it's not easy. In fact, to get this visualization, I had to filter a lot using our previous work from Federico Musciotto. I get rid of a lot of interaction based on their statistical significance as a definition from their paper. And yeah, I tried to visualize the data set, and I got this result, which is at least it's a picture, let's say, of the hypergraph. Of course, it's a mess because you have this group interaction that overlap a lot, so you cannot go that far in the visualization. We are trying to scale, so to have more nodes in the figure, more edges, but it's not that easy. So as of now, we settle for this visualization. Another thing you can do with HypergraphX is the dynamics. We have some contagion algorithms implemented, so you can play with this spreading processes on Hypergraph. These models are from this work from Jacopo Jacopini and colleagues. So you also have some like dynamics model for hypergraphs implemented in case you are interested in these other subfields of network sites. And something that we are starting to work on, that we have some work and we are implementing in HypergraphX is time. So we are also interested in assigning temporal labels to hyperedges. So encoding that an hyperedge is active at time 10 but not active at time 20, or that is active at time 10 and last for 20 minutes, for example, or 20 seconds, and so on. And so we also implemented some temporal measures for hypergraphs, mainly from the work of Luca Gallo and colleagues. But yeah, we are developing on this stuff. We are trying to have more general, more general hypergraphs as possible, also implemented in the library, and not only like static and undirected and so on hypergraphs in the library. So something very important, everything is also available as a Jupyter notebook, so you can play with basically every slide that I presented here. You have a notebook associated with it, so you can try every paper we implemented, every measure and package we have. And we are also working a lot on our collection of data. Of course, hypergraph data is not a lot, but since the interest in is increasing, we are trying to collect every data set that we have available. So we have a lot of data for face-to-face interaction. We have a lot of data of co-authorship data, but we are also trying to expand to more to other domain, and we are also trying to expand both to have more general data set to have like directed hypergraph data, to have temporal hypergraph data, and multi-layer hypergraph data. So to have a direction on the hyper edges, to have a temporality of the hyper edges, and to have like a type of the hyper edges as we mentioned briefly in our background part of the presentation. So speaking about the direction of temporality and type of hyper edges, I wanted to briefly discuss about our recent work on multiplex hypergraph. The idea here is that you have a set of hypergraphs. Each hypergraph is a layer in this case, and all the layers share the same node set, but each layer encodes a particular type of hyper edges. So as we were mentioning, each type can be associated, for example, to a different means of communication, for example, sending messages on WhatsApp or Facebook, as I was mentioned before. On hypergraphs, we have more examples. For example, each layer can encode a different scientific subfield in the physics domain, for example. So you can encode nodes, authors as nodes, you can encode papers as hyper edges, but you can also encode that each paper has its own associated physics subfield. So you have multiple hypergraphs. We have some other examples, for example, like EMDB data, in which nodes are actors, hyper edges are movies, and each layer is associated with a movie genre. You have high school data that we were using like in the traditional format, like standalone hypergraph, but you can see it as a multiplex hypergraph in which nodes are the student, hyper edges are face-to-face interactions, and each layer is a day of the week. In fact, the high school data involves 5 days of the week. So we can aggregate everything inside a single hypergraph, or we can treat day by day and having 5 different hypergraphs. We did this in a recent paper from my group. So I just wanted to mention some results. We have that here each vertex is, for example, a physics subfield or a movie genre or a day of the week. So each vertex is a layer in the multiplex hypergraph, and we connected layer, and the larger the connection, the darker the connection, it means that the two layers are similar in the sense that nodes in both layers share similar pattern of interactions in terms of their order of interaction. So two layers are similar if I have a node that is active in both layers and is active both at order 2, for example. So in both physics subfield, he wrote a paper with the 2 collaborators or 3 collaborators and so on. So we measure also this similarity in terms of the order of interactions. And also we were interested in the different patterns of interaction in terms of the size of the interaction. So we see that, for example, elementary particle physics has a paper of larger cardinality of atoms with respect to, I don't know, general physics, for example. But also that in the movie collaborators we have that on average every genre tend to involve a cast of like from 10 to 15 collaborators. And instead in the high school data set, since there is no reason that people change day by day their like overall patterns of interaction, they tend to like be, every layer tend to be similar to each other. And we see this also by their hyperedge size distribution. We have that in high school data set, we have like very similar hyperedge size distribution across the days. Instead, this distribution can be very, very different in the APS data set, so collaboration data set in physics, or in the MDB data. So we can notice fields in which you have larger amount of atoms, smaller amount of atoms, larger cast, smaller cast, and so on. Another interesting analysis was to understand how the degree of each node was spread across layers. And we measured this spread using this measure called participation coefficient, which basically is a kind of entropy. So how spread is the degree across layers. And so we wanted to measure if a node is like a generalist or a specialist, which means that a node participates in a lot of layers, so publishes in a lot of physics subfields, or if it publishes in a like one physics subfield or two physics subfield, but not a lot. And so we get interesting results. So like people were effectively divided in different classes of like spreading of the degree. So we had specialist node and generalist node in the real data. And like going higher order, we wanted to understand if also the hyperedge is connected like more generalist node or specialist node in the different layer. And we got that, for example, documentaries tend to be made by people making only documentaries, while family movies are made by people making like also participating in a lot of different movie genres, for example. Also in physics, we had that, for example, in nuclear physics, we had that people tend to be very specialized and participating only in paper in nuclear physics, while in other subfield, people tend to be like more generalist and connected in writing a paper in that domain. Instead, in high school, it's very trivial to see that like people tend to go to school every day. So every hyperedge basically links people that are always generalist because they participate in every day. Another analysis was like performing community detection layer by layer and measuring the similarity, the pairwise similarity of the communities inside each layer. And we got some histogram, like very hierarchical histogram, highlighting layers that had similar community structure and layers that had totally different community structure. For example, documentaries were totally unrelated with other layers. So while in high school, every day, I mean, the community structure was consistent day by day because people tend to connect with their friends and keep the same friends every day, basically. This measure are presented in our one of our latest preprint, and we are everything is also implemented in HypergraphX, so you can play with this and experiment. I think it's it can be promising to study new data set using this approach, because sometimes we lose information by aggregating everything in a single layer, but having multiple layers can give new insights on our data sometimes. And of course, multiplex hypergraph are not the only generalization of hypergraphs that is interesting. Of course, we can define directional hypergraph. So hyperedges are allowed to have a direction. So we have a group of senders and a group of receivers. As Carlos was mentioning, this is not the only way to implement direction. You can also implement direction in considering permutation somehow of the nodes in a set, so having an ordered set representing an hyperedge. As of now, we are focusing on this more like traditional network science perspective of having sender and receiver, but each data can be modeled in different way. We could model different aspects of our data, and it depends on our task what we want to encode and what we can discard as a complexity. And there are lots of data in which this can be useful. For example, I can send a mail to multiple people at the same time, or for example, we have some data set about Bitcoin transactions, so multiple wallet can send money to multiple wallet at the same time, so having a more complex structure of interaction in which you have multiple senders and receivers. Again, you can have temporal hypergraphs in which you assign a temporal label to hypergraphs, and you have a structure that evolves in time. And basically, you have the same story again. You can add more complexity, you can encode more information. Of course, you pay again the price of having more complex model, and you need to develop new algorithms, new tools, and so on. And a question that I'm trying to answer, or at least I'm trying to answer for specific data, is it useful to have these more complex models to analyze this data? And it's not clear the answer to that, in the sense that we are developing new models, we are developing new tools, and to encode more stuff. And sometimes it's useful to encode more stuff. Sometimes basically you can settle for more basic models. Even you can settle for traditional like networks in like graph theory sense. So yeah, it depends on the data. There are data sets in which I think it's fundamental to have like an hypergraph structure and possibly more general hypergraph framework. For example, an easy example is co-authorship data, in which papers are by design, like papers and authors that write papers together are by design an hypergraph, and using graphs is like leads to like losing a lot of information. So we are going on this line to understand what are the domains and the data set that really benefits from an hypergraph representation. And that's why having like ready libraries, I think it's useful, because it allows people from application domains to easily play with hypergraph and understand if they get more than like a traditional network framework analysis, let's say. So we are waiting for people to use our software and see what they can do with hypergraph, and if they get more like some nice insights on their dataset. So I think this question is really important, because we don't really want to developing new tools just for the sake of developing new tools. We want to developing tools that people actually use. So I think it's important to remember this stuff when like doing this kind of research. So like before closing this like small talk, I want to thank all my collaborators, because of course having designing a library is a whole lot of effort. So I was not alone in this. I had like a very huge amount of people collaborating and implementing their paper using this library. So I have Martina Contisciani, Caterina De Bacco, Leonardo Di Gaetano, Luca Gallo, Alberto Montresor, Federico Musciotto, Niccolò Ruggeri, and Federico Battiston. So this is it. I hope it was interesting, that you could now play with the library. Of course, we welcome feedbacks and discussion, and of course we are open to contribution, because the software is open source. So yeah, we usually accept pull requests and people contributing to the library if they want to. So yeah, thank you very much for the attention. If you have any question, I will be happy to answer.
All right. Thank you very much, Francesco. Any questions from the room here?
Yeah.
Sure. Let me bring the... You can do that.
Can you hear me?
Yes.
Okay.
Yeah. So thanks for the nice talk. So I would just try to get this started again. So you're saying in social or in network science, let's say, for example, I'm looking at a Facebook graph, I get some data, and it seems there's a design choice. Either I immediately code some substructures into hypergraphs, or I stick in the beginning with you were trying to explain the difference in practice between using a hypergraph versus using just a bipartite graph, right? And it seems that you are saying for some applications at least, it's useful to use it. Maybe if the information is anyways, if always linking to 3 people or always to 4, then rather than a bipartite graph, just use a hypergraph. So at least I'm keeping track which 3 people. But I mean, is that really such a conceptual difference than using bipartite graphs? I might have missed the point, maybe.
No, they are actually the same. Actually, for example, in my library, hypergraphs are implemented using bipartite graphs.
Exactly. Yeah.
So it's not like a conceptual different, but like I think there is no difference in these 2 objects, but usually problems are stated better using hypergraphs in network science. That's the only difference I have.
Just one question, because now then later in the talk you had sort of analysis of a data set then by counting number of certain kinds of patterns, but now we have hypergraphs. And one of the things that I find interesting, because actually bipartite graphs and hypergraphs are not at all on the same footings as data structure when it comes to manipulating them. So basically with a bipartite graph, there's no problem. I mean, if you have some entity which codes for a vertex, let's say of type A, which let's say is an actual person, and an entity of a vertex of type B, so the other type is a group, then there's absolutely no problem adding to a bipartite graph another person to a group. This is a perfectly legal operation I can take. I simply add a new edge of type A goes to B, right? While with a hypergraph, I would have to retract the original hyper edge, let's say with 3 members in the group, and create a new one with 4 members in the group, correct?
Sorry, I didn't get really the question.
I'm trying to model a process where I manipulate my social network. Maybe it's me, maybe it's a temporal process, where basically a group grows by 1 member. I have a group of 3, in your language, call it as an undirected hypergraph of some cardinality. Now I'm adding a new member in the group, certainly completely fine operation. And the bipartite graph is an absolutely well-defined graphical operation. I just simply make a new edge between an A and B type vertex. Now in the hypergraph encoding, now I suddenly have a hypergraph edge of cardinality 4, right? So it seems that the difference between the 2 is in one case, I do not pre-configure any cardinalities. I simply say I have a cardinality, perhaps finite, of each group, and then I can freely add or retract edges into that. On the other hand, if I do hypergraphs, I seem to explicitly track having the exact cardinality of a group. And now what I found interesting is that now if you count patterns, it is not at all the same thing of saying, is a group having at least 3 members? It's a different question than whether it has exactly 3 members. And so, I mean, maybe you are not realizing it, but it would perhaps be interesting to contrast the two things. In your experience with the data sets you had, was it really an advantage to be able to count in this way exactly groups with exactly 3 members versus, groups with at least 3 members? That's a different way of counting, right?
Yeah, no, in okay, this is like I think more a way, like a difference in the way we state problem with respect to a difference in the way we represent our data, in the sense that I think in the case of motifs, for example, you care about, I don't know, counting patterns with this shape. So the 6 patterns I have in these slides. So in traditional network science, the problem of motifs was stated like this, and it was very trivial to generalize to hypergraphs, and that's what we did, and that's why we stated the problem using hypergraphs. But
I'm not questioning your reason. I'm only saying it's an interesting observation that you say there's a advantage in this way of counting, because I mean the main question is, of course, typically your networks might come from a dynamic process or from temporal observations of data. And I mean, now it's really a difference. In the hypergraph setting you can say something like, I see a process where if I have a hyperedge of exactly 3 members, I can get a hyperedge of 4 with a certain frequency. In the other setting, you could say something more general. You could say, if I have a group that has at least 3 members, I have n members, then I have the threshold to do a transition. So now the interesting question is, in actual life data, maybe I should have rephrased the question. Is it really that you see scenarios where it's advantageous to have this exact counting implemented with hypergraphs? I mean, is there data sets which are better modeled with these kind of hypergraphs than hypergraphs?
In my experience, I think they can be equivalent representation, hypergraphs and bipartite graphs, in the sense that it depends on how you see the problem, and the way you want to attack your problem can be better explained using hypergraphs or bipartite graphs, but you usually get the same results at the end. So it depends on how you define your operation on both. So yeah, for example, in this problem, I count hypergraphs, but on the back end in my software, actually I'm using bipartite graphs and I'm converting between the two. So from a narrative point of view, it's easier to represent the problem using hypergraphs, but like from, I think, a representation from point of view modeling, they are the same, using at least like representing real world data. They are equivalent usually, and this is my experience. But
no, I mean mathematically no, but I mean apparently in your
mathematically I think they can be different, but like when you represent real world data,
What I mean is that the way you count patterns is maybe the better question. And I mean, what you mean by an embedding of such a kind of hypergraph you're showing into a graph is probably that you count one hyperedge disregarding, because you said you have a set. So you must have an algorithm which tries to complete somehow. You take one base vertex and you try to search, is it contained in some bag? And I mean, you don't count an edge more times. I mean, it's not a monomorphism. It is something else. You just pick the set and don't count multiplicities. While if you had an hypertype graph, then it would matter in which order you match the edges, so you would get multiplicities that you would have to divide out again.
But that's why he said that how he codes order.
That's the point. Yeah.
Exactly.
Yeah, because
Sorry.
no, for me they have like a very specific name, the nodes. So a node is a unit in the system in a bipartite graph, and a node is an edge in the system. So in like my representation from like a structural point of view, like computer science point of view, this is equivalent, but like I think mathematical they can be very different. But if you, I think, label the nodes as unities and label the nodes and edges, and you fix your like semantic, they are equivalent.
But again, like, I mean, the key point is once fixing the data structure, you are fixing also the kinds of analysis you can do on temporal graphs at least. Because I mean, now you are essentially telling us, I mean, again, imagine you wanted to understand the functioning of a social network. Now you're pre-configuring that transitions you can have are necessarily of type a hyper edge goes to hyper edge. It's a basic example. While in another setting, you might permit an analysis which says, on average, the statistics of, I mean, the way a group grows is it has to have so and so many people exactly, or at least so and so many. I'm only saying that it's basically a question of what are you going to do as a type of analysis later, because you're only providing us with this way of pattern count, right?
Yes. Yeah.
Do you understand the question? Or?
Yeah. It's very like task dependent.
Is it useful? Is it in social network analysis, for example? Is it in temporal social networks, for example? Have you experimented with this?
Yeah, there is. I mean, not me personally, but there is like a paper from these guys here, Jacopo Jacopini, that experimented with the temporal hypergraphs and group formations in hypergraphs. But yeah, the idea is basically that groups can grow in time, and you can add one node to an interaction. For example, you start by an interaction of size 3 and you get a new node and it becomes an interaction of size 4, and they study how this happens in real world data. So yeah.
And it was really useful in that setting, not just, I mean, of course you can map. I mean, my difficulty is that I can, of course, take a bipartite encoding of the thing, where the process is really just take any group and, you know, take any member, not yet part of the group, and add one single link between them in the bipartite graph. And from the outside world, it would look like I have a bunch of transitions. For each possible cardinality first, I get one more cardinality. I have to completely remove, so I have to make a new one. So these are two completely different encodings. And this could produce an artifact in the analysis, no?
I don't know. I think it depends on the semantics you give to your bipartite graph and to your hypergraph. Usually, the way we use bipartite graph leads to, I mean, for the way we think about bipartite graphs, they are equivalent. So it's equivalent to add a new edge or construct, like saying that an hyperedge of size 3 destroys and creates another hyperedge of size 4.
I mean, I don't know, you probably missed the first, my talk.
Yeah.
Yeah, so I mean, the interesting question we had there is that basically if you look at real-life systems which come from some sort of transition sequences on the states, I mean, like a social network evolving, there's some elementary operations involved, of course, but I mean, typically you see a bunch of operations having happened in observation intervals, so you have no idea what are the internals of, I mean, you could have the atomic transitions, but you see typically a compound transition of some sort. And then you might ask for a model that produces your data, right? Maybe some mechanistic model that says a certain sequence of transitions is necessary to form a supergroup or whatnot, you know? And I'm asking more about the kind of experimental data that you have seen in working with this, that motivated you to pick this particular, I mean, very sort of explicit coding of, let's say, degree structures and whatnot. Was it something that is really important in applications, or was it implementation-wise efficient?
What do you mean by applications, by the way?
I'm wondering if there's, for example, in people trying to model social networks.
I mean, like what we were showing, Francesco, maybe you can show the paper of yours with Federico, like the one where you dissect, the one where you have motifs in social networks, in bio networks, in authorship networks. And it seems to be indeed, if maybe he would be using your definition of this motif, that would be actually really using these patterns, one would dissect and they would fall into two different categories, social networks and the other, the non-social networks. You know the one from 2000?
Yeah.
Right, I think. Do you have the link? Maybe that kind of...
I mean, I'm only surprised because for example, in biochemistry, which is of course not social sciences, but there, for example, it was quite important that the kind of data structure that really models most of biochemical reaction is not technically just a hypergraph, but something where you have also a notion of sub-hypergraph, let's say. So a hypergraph where you can speak about a partial embedding, but a hyperedge is not fully specified, let's say. So it's actually akin to a certain version of hypergraph. So I was just surprised that hypergraph in this particular way, just bags, seem to play a technical role in this analysis, which is interesting.
Yeah.
I think, can I try to rephrase your question so to make sure I understand and maybe to possibly make it clearer?
Okay.
Is it, you're asking why or what data motivated use of
advantage
of hypergraph over bipartite graphs? Okay.
Yeah, or like even this point, Nicolas, so I read, I mean, there were indeed like it's a bad way of putting that, but it seems to be that what you're saying, that there would be also an extended number of ways to generalize.
Or said otherwise, on states, in concrete graphs, I see immediately you can map one into the other. They have different features. I mean, as I said, subgraphs of a bipartite graph have exactly this feature that you can speak about a constituent in what would be a hyperedge otherwise. So, I mean, you have a finite mathematical notion because you have more ways of embedding things, but for maybe the representation of the data, this could be precisely equivalent, of course. But then once you look at dynamical systems, you look how systems change and how, if you want to analyze how steps can occur between changes, this is an extremely different data structure, also mathematically. So, because exactly of these differences in what you can call an embedding. So with a back hyperedge, you can speak about vertices that are incident to it, but you cannot say anything further. While with bipartite graph, you can speak about each of the ways an edge is incident, vertex is incident. So,
but what does it mean, like in a bipartite graph, to be incident for an edge? Because, like,
let's take a directed bipartite graph for simplicity. It is easy to say that if you have some type of vertices modeling groups, for example, and some others modeling elements in the group, then you can say, first of all, which element is part of the group by simply asking is a relationship. But then also you have to compute the cardinality of the group by counting the number of linked edges. While in your back model, it is just explicitly given, right? In the data structure, you favor a presentation where you directly know the total cardinality of that edge, hard-coded. So while in the other setting, group type vertices are just that. They're just a kind of vertex. You don't have any a priori information of what is the concrete degree of that. That only gets manifested once you are in a concrete graph. And now if I look at manipulations of these, you do not have to break any structure at all. You don't have to remove these group vertices to add a new element. You can keep the exact same entity, just add a new link. While with a hyperedge, you would have to remove the hyperedge, make a larger cardinality hyperedge. You see what I mean? Right?
Yeah, but
And now if you try to come up with a model for a dynamical process that at its root does perhaps nothing else but changing group sizes, then one version in the bipartite world would have an extremely simple generator, which is just take two people, one of group type, one of element type, and link them or unlink them. This way you can get a dynamical process that can at random generate group sizes. Or you say the version in your language, which would say you have to get a list of possible transitions, one for each input degree of hyperedge. And then maybe you say, in my real life example, I only have ever degree 3 go to degree 4, maybe some selection of cardinalities. This is an extremely different analysis, right?
Yeah.
You see what
but I think, maybe like from a mathematical point of view, No, I mean, maybe there is like.
Because this is very specific to the writing, right?
Yeah, I mean, I'm not really into like dynamical system, but the question, I mean, the way I understand the thing is that we don't really care about this, like, I mean, usually in application, at least in the dataset that we have, for us is the same to represent a dataset using a bipartite graph and an hypergraph. And you can always state the problem or the task you want to analyze using both languages. For example, here, if we want to understand what are the most frequent patterns in a large hypergraph, I stated the problem using the language of hypergraph because it was easier to translate from the old problem in network science from graph to hypergraphs. But the same problem could be stated using bipartite graphs. And you add in that case frequent patterns of bipartite graph, and you could always reconstruct from like a small bipartite graph as a small hypergraph and vice versa.
I guess Francesco, that their models are sort of more intended for static representation, right?
I think that was my main question.
Yeah, I get it. I understand.
And also weighted versus unweighted. And we discussed a bit, Francesco, about the colored, non-colored, because in this case also these motifs could be, we could list them and dissect the network or hypergraph even more if this is needed.
Yeah, of course. The question is always if something is needed, because on top of hypergraphs, you can add a lot of information, like putting like a single weight to every node in HyperEdge to see how much every node contributes to the HyperEdge. And in that sense, I think like what we were discussing, like of the difference between bipartite graph and hypergraph, they disappear when you have like a computational framework in a computer where you can add information and treat an hypergraph in the same way you can deal with bipartite graph and vice versa. So if you care of weights for every node that participate into an HyperEdge, you can just add an attribute to a variable in a computer. You don't need like a bipartite graph. But I think from a network science point of view, you benefit from a clearer statement of the problems using hypergraph.
Yeah, in the talk before, I also discussed this question a little bit, just because indeed in the way how you encode, it depends on how you can kind of pre-code the answer to your question when you define this representation of the hypergraph, because in a way that when you are starting from your social, technical, and quartership network, and I was putting your paper as an example of it actually, that in a way when you, depending on how you encode it, also then you will decide in the answer if your question will be different in a way. You kind of decide how much of the information you put and encode in the bipartite, in a line graph, or in a click graph, or in hypergraph. And I mean, sometimes there would be information reduced in this representation, right, of a hypergraph. I don't want to repeat already, we discussed it enough, I think. Yes, I mean, it's not, for me, it's just a comment, sorry, just for that. We will send you the recording.
It's on YouTube.
Yeah.
Okay. So there's a question, maybe this further clarifies the discussion from my colleague at the Wolfram Institute, saying whether the hypergraph algorithms that you're running reduce to a bipartite graph with adjacency matrix representation and just linear algebra. And I'm curious about the details of how much, because exactly in this translation, so for example, I'm thinking about motif matching, just to count motifs, how you deal with, for example, the redundancy of symmetry And if you had these two representations, that would matter, right? When you do that kind of matching, if you had a sort of native set matching, or you had to do actual click matching of the motif. So yeah, any insights on how you undertake?
No, I think we have some I think different, sometimes interest in the way we state problems. For example, in my case, motifs are just like patterns of sets in a data structure. So in that sense, I use multiple data structures as I need to store my data in a computer, and I use bipartite graph, but I also use adjacency metrics and so on to query efficiently my data structure depending on the subtask I need in my algorithm. That's why I was mentioning that in my way of seeing things, bipartite graphs and hypergraphs are the same, because when you put in a computer and you want to perform your task, basically they are the same. And also my algorithm, for example, for counting motifs, is just like an iteration over sets, and very efficiently the subsets in a larger database of sets. So yeah,
we are doing that also because in Python, also it's specificity of Python, right? That with sparse matrices, it's faster to do some things this way.
No, it depends really on the subtask you want. Like I developed my own data structure from scratch to have like consistent and multiple representation of the data at the same time. And for example, if you want to get the neighbors of a node, one data structure is more efficient than the other. So you don't, like, for example, you don't have like just to give an example, for this task I would use like maybe a bipartite graph and not a matrix, and maybe there are tasks in which I use vice versa for the same for other subtasks. So yeah, to deal with hypergraphs, I use multiple data structures at the same time. Each data structure captures different aspects of the data, and I can query fast what I'm interested in for the task.
Thank you.
One final question. Anyone? Specific? I wanted to just, out of curiosity, specifically what data structure you use for the algorithms for hypergraph isomorphism and the motif pattern detection and so on. Like, how do you deal with for example, the redundancy of the symmetry? This is something that we are working on at the moment to encode more general data structures as edges in our own software. So curious to know how you deal with particularly the redundancy of the symmetry of a set with another set, because I imagine your elements are whatever characters, something that have unique IDs or something like that, or not necessarily?
Yeah.
Okay.
No, basically, in a very like naive way, in the sense that since I want to compute isomorphism between really small sets, I try every possibility and to see if there is one match.
Okay.
Yeah. Because I care more about like the feasibility of an algorithm for like an implementation point of view. I'm not really into like mathematical problem of isomorphism. So this was the most efficient way of solving the problem from like our specific task, and like also like time spent on writing code efficient point of view.
Okay, and so specifically, I mean, just to get a picture in my head how it works. how do you deal with just having permutations of the same? I mean, do you have a set specific match function that just out of the box, or you do something specific to deal with the, permutation redundancy of a motif that is just a set?
Mm-hmm. Yeah, the idea was actually very, I don't know how to say, very programming idea, in the sense that I store every hyperedge as a list in Python, and each pattern is a list of lists, because in a pattern you can have multiple hyperedges, so you have a list of lists. Mm-hmm. And basically, if you sort your list in some way, you just need to look all the permutation for the IDs, but the sorting will remain the same, and you just need to check if two lists of lists are the same after reordering and querying all the permutation. Okay. So, for example, if you have a list of one list of size 3 and one list of size 2 in Python, if you sort this list, they are reversed. So you will always have a list of size 2 and a list of size 3. So if you perform this sorting, whatever your list of lists is, you know that you have the cardinalities of the list sorted, and then you only need to check all the permutation for the IDs, and you will have that at some point you will have two lists of lists that are totally the same, and you just need to check.
Yeah. So my question then, basically, just to make it very concrete, do you have to basically divide? You define all the permutations and then you divide by the order of the permutation group, or do you do some kind of pattern matching that some canonicalization or something that allows you to basically not count all the matchings and just do one match per edge?
No, yeah, basically it's a form of canonization, but it's not very formal. It can work only with patterns of size 3 and 4, because then it explodes. Yes, that's why I was mentioning that I'm not really into the mathematical details of the problem. We cared only on the feasibility from a computational point of view.
Okay, I see.
I mean, that was sort of my question, because of exactly this extreme explosion if you don't use a well-adapted algorithm of n factorial analysis of permutations. I once heard, I'm not a social scientist, but I once heard that in realistic social networks, there's this pretty hard limit of 135 people who are sort of the largest social crowd you really interact with. So that is a high degree away from 3. And I mean, also in chemical networks, we have the same problem. We might be limited for carbon by 4, but so that is okay. So when I would do a hypergraphics more for this whole matching would probably explode for me.
Yeah, but for example, in this case, the problem was actually to count patterns of size 3 and 4. So that's why we could do that, because it was by definition of the problem counting patterns of size 3 and 4, because the idea was to understand systems in terms of their decomposition in patterns of small number of nodes, and have a sort of fingerprint of the system. This fingerprint here, basically.
Okay. All right. Yes. Well, I think thanks so much, Francesco, for all the details. It's been a long day. Sorry for the delays, but yeah. Thank you.
No problem.
And we'll see everyone tomorrow at the same time. Thank you.